Hi everyone, in this video we are going to solve or revise all the topics that might come across in your IGCSE physics exams tomorrow, and this is basically all the topics that I think are important for your exams tomorrow. Like this entire PDF compiles all the repeated questions that you guys have faced in the recent past papers. So for examples like loudspeakers, transformers, right, these are the concepts that they always ask in your question papers. So I have compiled all those topics in this PDF. So by solving this PDF or actually watching this video, we'll actually clear all the concepts related to those questions, and we'll obviously write the answers using the mark scheme points for this PDF. And if you want to get this file, you can either WhatsApp me directly in this number or you can email me in this email address. I'm very much active in WhatsApp but quite less active in email, but I'll still obviously try to reply fast as I can. Okay, so these are the ways you can contact me directly, or if you want to have if you don't want to individually text me every time I upload a video or a file, in that case you can join our Discord group. For our Discord group, every time I will upload a video, we'll automatically get the link for that video in the Discord group, and also the file for that video will be uploaded in the Discord group automatically. So if you want to get files of my next upcoming videos for your A levels also, you can obviously join our Discord group. And not only the videos, only the resources that I will upload in my videos, there are also some other resources, some private resources that I usually give to my students in the Discord link also. So the Discord link is actually available in the description of this video, and if you still can't understand or if you still can't find the Discord link, then again inbox me in my WhatsApp. I will send you my Discord link there. And another thing, since your IGCSEs are coming to an end, obviously the next chapter is going to be A levels. I am actually hosting an A level trial class on June 20th after all of your IGCSE exams will end. Our classes will start from mostly June end or July 1st, but this is the trial class. For the trial class, we are going to explain how many units they have in A levels physics, how many units they have in A level maths, how many units they have in A level further maths. Okay, all of these things will be explained, when you can sit for the exam sessions, how these exam sessions sessions should be planned for your exams times and for your understanding, and how can you understand which session will be better for you. And then again, how will I teach A level physics and maths, what are the resources I'm going to provide to my students, and what are the things which I'll make available for my students. All of these things will be discussed in our trial class for June 20th. So I would suggest join our trial class. This is obviously a free trial class. You guys do not have to pay for this. This is like an introduction for A levels and introduction for my AS physics and maths classes also. So if you guys are interested, please let me know. I will certainly give you the link for my classes. And again, if you are interested to join our trial classes, then you have to again inbox me in my WhatsApp. This is my WhatsApp number. By dropping a message in our WhatsApp, I will obviously tell you much more details about the trial classes, like what timing and what how much duration the trial class would be, and what are the contents or PDFs that I would want to give you before the class, so that you can go over those and then attend the class, which will make it much more easier to access everything I'm trying to say within the class. And again, all my classes are online, so anyone from any place can join. So far, I think there are people from Qatar, Sri Lanka, Turkey, Kuwait and Dubai starting my classes. So if you guys are interested from any other places, let me know. You guys are obviously certainly welcome to start my classes. So let's start with our physics revision this time. Now this entire PDF is serially arranged. We're going to start with the basics, and then as we move on, we will come across wait 1 minute, let me just use this. As we move across, we will come across electricity, energy, then waves, then this is electricity, then electromagnetism, and then you have your lastly atomic structure, fission, fusion, right? Okay, so we will start now. We'll start with movement and position. Obviously, we understand that speed is the distance traveled per unit time. Now, sorry, I made a mistake. I used double L over here. This is supposed to be in single L. Just cancel this. I actually made this PDF in a very much hurry, so made a mistake. Okay, now this equation actually over here is speed for distance traveled by time. That can again be used for velocity also, because at the end velocity is nothing new but a vector quantity version for speed, right? This is a scalar quantity. which means it only has magnitude, and this one's a vector quantity. That means in addition with the magnitude, they have directions also. And directions. Okay, now over here for this case, so many people, so many students of mine also, they don't understand what magnitude is. Magnitude refers to the value, the size of the quantity. For example, a car is moving with 25 meters per second, right? This 25 is the magnitude of that quantity. The size or the numerical value for that quantity is known as the magnitude. Okay, and then again from this part, all of the quantities should have their own unique unit. Speed has a unit of unit meters per second, because this is basically what? Distance over time, right? Distance is measured in meter, time over seconds, time in seconds, so it eventually becomes meters per second. Same thing goes for velocity, as there's only one difference between velocity and speed, that is velocity only has directions. Other than that, without direction, velocity is entirely same as speed. So for velocity, the unit is still same, meters per second. For velocity, the equation is also same. For speed and velocity, if you write the equation in terms of symbols, speed is also actually referred as v, velocity is also referred as v. This is the symbol for the quantity itself. Both of these quantities, speed and your velocity, both are actually referred as v, or they have their symbols small v. We cannot use s for speed because s is used as displacement in equations of motions to represent displacement or distance. Okay, so we cannot use s for speed over here. Another thing that is we can do is for this speed or for this velocity, the equation is entirely similar. Only difference is that on the numerator it doesn't have distance, it has then displacement, right? Because of displacement, again velocity becomes a vector quantity. So let me write down the equation if in terms of our velocity in detail. Velocity is basically displacement traveled or displacement over time taken. Now we always use a dot multiplication to understand if a quantity is a vector or it's a scalar quantity. In order to understand dot multiplication, I'll just use a box over here. For dot multiplication, we use this method. Again, dot multiplication is not actually required in your IGCSE knowledge. This is mainly, I learned this from my undergraduation, where we can actually understand if a quantity is vector or scalar using matrix also, right? So we're not using that, obviously. Matrix calculations in IGCSE physics or in A-levels physics, they're not needed, and they're quite lengthy and complicated, so that's why I do not use that in my IGCSEs or IAL classes. But dot multiplication is also a concept I was taught in my undergrad classes, and I think that was quite easy to understand for the IGCSE IAL classes also. So I'm going to use that to explain how can I understand if a certain quantity is vector or scalar, because memorizing for me is not that much a convenient process all the time, and also there are a lot of quantities that I need to understand if they are vector or scalars, right? So how many quantities I'm going to make a list for that, which one is a vector, which one is a scalar. One easy thing we can do is that we will assume all the scalars as positive and all the vectors as negative. Now using this assumption, we can identify any quantity if that quantity is a vector or scalar. For example, I obviously have to be provided with the equation for that quantity. For example, now if I start working with force equals to mass acceleration, where mass is a scalar, I already know because mass doesn't have any directions, and acceleration is a vector. So their product would be positive multiplied with negative, eventually becomes negative. So the final sign for force from its equation turns out to be negative, which means that this is certainly a vector quantity. Right, this is how you do dot multiplication to identify if a certain quantity is either scalar or vector. Okay, I would suggest do this on your exams also if you are not aware if a certain quantity is scalar or vector. Okay, other than that, there's nothing much more to understand from speed velocity. One thing is important over here is your speed is mainly scalar because of distance. right? And your velocity is mainly vector, is because of displacement. Always remember that speed doesn't, distance over here doesn't actually have any directions involved. For example, if I try to find out the distance between point A and B, okay, that will be basically the length between any 2 points. But for displacement, it always has to be the shortest distance between 2 points. It always has to be the distance in a straight line, right? Whenever there's a turning point in displacement, the value changes. For example, over here, if you start traveling from A to B and then return back to A, your distance would be twice AB, right? Whatever the length for AB is, your distance would be twice AB. Maybe the length for AB is 5 meters, then distance would be 2 into 5, that's 10 meter. But for displacement this time, displacement cancels out whenever the direction changes. For example, if I'm considering the direction towards right as positive, in that case left would be negative, which means that if I'm going to travel from point A to B 5 meters and then again reverse my direction and start traveling from point B to A, it will cancel out my values. 5 meters towards right and 5 meters from left will cancel each other, and eventually at point A, when it will return to point A, the displacement would be 0. So that's why it is known as displacement as a vector quantity, because for displacement, whenever the direction changes, the magnitude has to be assigned with a negative sign in order to indicate the direction, and because of the negative sign, it will start cancelling out some original value, right? So 1 minute, I should write this down over here. For displacement, it always has to be the shortest distance and in a straight line. So this has to be shortest distance in a straight line. Okay, now then we'll move on. This is the concept for your speed and velocity, everything you need to know for these parts. Other than that, nothing else. We'll move on to acceleration now. For acceleration, it is the rate of increase in velocity. Now not exactly rate of increase in velocity, better word over here would be rate of change in velocity. Okay, why is it rate of change in velocity? Because acceleration can also cause velocity to decrease, and whenever velocity decreases, your object is decelerating, that is negative of acceleration, right? So in most of the cases, yes, whenever the object is accelerating, doesn't matter at what rate. If your object is accelerating at a constant rate, at a changing rate, at an increasing rate, at a decreasing rate, in all the cases, object's velocity always increases, right? So that's why maybe I wrote that rate of increase in velocity. Another thing over here, the term rate actually identifies as a hidden quantity itself. Rate indicates that your velocity will always be compared with time, or over here velocity over time, velocity divided by time. Original equation for acceleration is again change in velocity over time, which is basically what? Final velocity minus initial velocity over time taken. Now I have included a diagram over here. This is your diagram of, this is the start of your diagram and this is the end of your diagram. At the starting point, you have your initial velocity, which is referred with small u, and at the end of your diagram you have your final velocity, which is referred with v over here. And in this case, if I want to express the equation for acceleration in terms of symbols, this is how it will be expressed: v minus u over t. Right, and then you can easily calculate the value for your acceleration by inputting the value for your v and u and t in the given equation over here. After this, again let me explain that in what cases your object's velocity increases and in what cases your object's velocity decreases. Now velocity increases in all cases as long as the object is accelerating. Acceleration could be in 3 states. Okay, let me explain that it could be either in constant rate, or it could be in a increasing rate, and then it could be in a decreasing rate. Decreasing rate doesn't mean that your object's acceleration is decreasing. Okay, all of these cases will actually lead to you velocity increases. Okay, and in only one case your velocity decreases, that is deceleration. Whenever your acceleration becomes negative, only in this case your velocity decreases. Now let me explain what these three statements over here indicate. For example, in constant rate, I'm going to draw three scenarios for a car. This is the same car in three different positions, A, B, C. Over here, if your object is moving with constant rate acceleration, this indicates the value for your acceleration is going to be same for all the three scenarios. This is known as constant rate acceleration. If you're working with increasing rate acceleration, then this indicates that your value for acceleration increases over time. Previously, if it was accelerating at 5, now it will accelerate at 10, and then it will accelerate at 15, right? Now we can clearly see that your rate for acceleration increases over time. For this case also, velocity increases. And then again, decreasing acceleration indicates that over time your velocity, I mean your acceleration should decrease. So maybe at the start you have 15, then 10, then 5. So this one indicates your value for your acceleration decreases over time. And it still is not deceleration, right? The value for your acceleration, you can clearly see, is still positive. So your object is still accelerating but at a decreasing rate. And whenever your object is accelerating at a decreasing rate, velocity still keep on increasing, right? So these are your three scenarios which you have to understand how your velocity is related to acceleration. How even though acceleration is not always uniform, but at increasing rate or at a decreasing rate, velocity will keep on increasing. Okay, so this is very important point over here, and only in one case your velocity decreases, that is when your object has a negative deceleration, or when your object has negative acceleration or deceleration. If you're writing deceleration, then if you do the calculation right from this part, your acceleration has to be written as negative, right? But if I'm going to write it as deceleration, for example, I got a value for negative 23 meters per second square, right? But then again, if I wrote deceleration, then I do not actually need to write negative in front, because negative already, deceleration already accepts the fact that this is negative acceleration, right? Then you do not need to write the negative in front. Also, another thing to keep in mind, that at constant velocity, object cannot move with acceleration. At constant velocity, the object's acceleration has to be 0. Okay, that's because over time there will be no change in v minus u. Like for example, if your object has the same value for u and the same value for v, in that case v minus u turn out to be 0, right? And if your numerator turns out to be 0, obviously the entire value would be 0. So there will be no acceleration if the object is moving with constant velocity. One another important point over here to understand. So 1 minute. Acceleration is 0 meters per second at constant velocity. Now these are very important basic things to understand, because they would ask you questions regarding these simple things a lot from your question papers. Another thing over here, for acceleration, their unit is meters per second square. Okay, so for acceleration I'll write their unit is meter per second square, and their unit is like this. Symbol over here is small a. Capital A only represents area, small a represents acceleration over here. Another thing again, if you want to find out the difference between deceleration and acceleration, in acceleration final velocity is always greater than initial velocity, and in deceleration final velocity is always smaller than initial velocity. I should write this down over here. Acceleration, deceleration. In acceleration, final velocity always greater than initial velocity. For deceleration, initial velocity always greater than final velocity. This is always a positive magnitude, this is always a negative magnitude. The final answer you will get should be negative. Okay, and yeah, this is it. This is like a notes, mini notes over here for the difference of acceleration and deceleration. Okay, other than that, your unit 1 also have equations for motion. Another thing to understand, there are actually assumptions to include these equations. Okay, for example, the equation that you know for this one, okay, v minus u over t, this is actually a derivation of this equation. For example, from this part, if I make a the subject, okay, then it will be what? I'll first flip the equation and then make u to the right hand side, and then finally make a the subject. That would be v minus u over t. So basically v is equals to u plus at is a derivation for the equation for acceleration. Now, right, now in this cases, the two equations of motion only can be used when your object is moving with uniform acceleration. It can never be used if your object is moving with changing acceleration, increasing acceleration, or decreasing acceleration. Okay, it can only move at constant acceleration. So there's very important assumption for this, that is assumption is constant acceleration. Now, I remember asking my students after explaining entire physics that what are the equations for constant accelerations, and they were quite confused that why and where did that came from. I remember Oliver and Akib, they were like extremely messed about these things, that where is this equations coming from, where am I asking these questions from, even though I explained these equations right a few minutes earlier to them. But problem over there is that we as a teachers, we forget to highlight the assumptions for these equations. All the equations in your IGCSEs or in your A levels that will come across in physics, they always have assumptions, because in real life or in mathematical life, they are two different things. So that's why your objects or all the equations should have like assumptions involved in them. For example, for all these equations of motion, the assumption is object must move with constant acceleration, right? So this is your assumption, very important assumption, that object must move with constant acceleration. If they are giving a situation where the acceleration changes, then you have to break the scenario into two sections, up to which the acceleration is constant. For example, if an object is moving with 3 points, is moving between 3 points is moving between 3 points A, B and C, and the object's acceleration was constant between A and B, and then again it changed between B and C. So in that case, you have to consider separately the sections A, B, and then again separately calculate the section B, C. Over here, you cannot take this entire journey as a whole, because acceleration was not constant. If your acceleration changes, then you have to break down the journey into two sections, up to which the acceleration was constant. I hope the concept was clear. And then again, there's another assumption for this equation also, v is equals to dt. The assumption is object must move with constant velocity. If your object is not moving with constant velocity, then you cannot use equation v is equals to dt for these two cases. So again, over here I'll just write constant velocity, and this is your assumption. Okay, so we'll move on. I think this is the end for your kinematics part. We'll move on to your graphs section now. I'll zoom out so that you guys can see this entire screen, all the things you need to know, and then we'll move on. Okay, now these are the two graphs that were also discussed in your chapter 1, movement and positions. For there are two types of graphs, distance and velocity time graph. There are actually in general 5 types of graphs: distance time graph, displacement time graphs, velocity time graph, speed time graph, and lastly your acceleration time graph. As we move along to the next session of your life in A levels, you will come across with velocity time graph, speed time graph, acceleration time graph, displacement time graph. All the other 3 types of graphs will be included in your A level syllabus, but for now, for IGCSEs, we are only going to discuss with distance and velocity. I mean, other types of graph are also introduced in IGCSEs, but they would never ask questions regarding those topics. Like I rarely found questions from speed time graph or acceleration time graph in IGCSEs. Okay. So these are the most common type of graph, and these are the also most common types of shapes. So understand the shapes very clearly over here, because this will be extremely important for your exams tomorrow for both paper 1 and paper 2. Now over here, this is distance time graph. You have to always understand that why we keep distance on the y-axis and why we keep time on the x-axis. That is because on x-axis, we always draw the independent quantity. And on y-axis, we always draw the dependent quantity. Okay, over here, in case for the relationship for distance and time is obviously the independent quantity, right? Time will always go on, doesn't matter if you do the experiment or not, but distance over here is a dependent quantity. For example, if there is a 1 kilometer distance, you obviously cannot travel that within 1 second, right? So there's a minimum amount of time that must be provided to you to travel that distance. So time over here is the independent quantity and distance is your dependent quantity. So now in this case, there are 5 types of graph, as you can see. For distance time graph, these are actually scalar quantity graph, so they will be never include with a negative axis. For all the cases, even if it changes directions, it will always remain on the positive axis. So this is a positive axis graph, that is important to understand. Positive axis, sorry, wait 1 minute. Positive axis, because this is a scalar quantity graph. Okay, now after this, again let's understand the shapes for the following graphs. For example, for the first graph over here, this indicates that distance is same but over time is increasing, right? As you can see, time is increasing but distance remains same. In this case, I'll just explain, like write this over here somewhere, that time increases, d same, t increases, wait, I should use a thinner ink over here, 1 minute. Increases but d remains same. This is for a stationary graph. When an object is at rest or stationary, this is how the graph would look like. So this is this name for the graph, or I'll just write the names for the graphs over here. Okay, A represents stationary or rest graph. Or rest graph. Now for B, again, these type of graph are known as constant speed graph. Why is that? Because this is a what? Straight slant line, right? For straight slant line, if you can calculate the gradient, you'd see that gradient for every point will be same. As the gradient for every point is same, and for distance time graph, the gradient will always give you speed, because gradient calculation is what? Change in distance over time, and change in distance over time is actually the equation for speed. In that basis, as over here along every point, along every section of the graph, as the value for your gradient remain constant, as this is a straight slant line, so over here the name for this point B graph is known as constant speed graph. Okay, so this is again a quite important working for this equation, for this graph. So part B is constant speed graph. Then again for part C and D are quite different. For example, part C and D over here, as you can see, initially the graph is more steeper and finally the graph is, so initially it's less steeper and finally it is more steeper. How can you understand if a graph is more steeper or less steeper? By the inclination of that line. For example, over here, this one was less inclined than the red one, right? So over here, the red one has a higher gradient than the blue one. Obviously, at the point, they would all travel with the same gradient. But for example, if the gradient for graph A was 10, then the gradient for graph B would be 2. Right? In that case, for the point B graph also, this one indicates that object A has a higher gradient than object B, as the shape or as the line of your graph is more steeper. Right? There is also one indication for this part, so I will just explain that object A has higher gradient then object B. Object A has higher gradient than object B, right, as it is more steeper, as its graph is more steeper. That is an explanation for point B graph. Okay. Other than that, now let's move on to graph C. As we can see, this section is what? Less steeper, and this section is more inclined, so more steeper, right? So over here, as the steepness of the graph increases, this indicates that the velocity over here was not constant. Over here, velocity was at a lower rate, and then in this section, velocity was at a higher rate, which indicates that over time, velocity increases, and if velocity increases, the object must be accelerating, right? This point of, obviously over here, this is a distance time graph, but at the end, the speed and velocity and speed and velocity, they're quite same. So we can see that over here, the object is not moving with constant velocity anymore. It is now moving with increasing velocity, right, or increasing speed. That would be a better option over here, a better choice of words, that over here the object is moving with increasing speed. So in this section again, for part C, this is known as increasing speed, as the graph becomes more steeper with time. Lastly, again for D, this is the opposite of C, right? Initially it is more steeper, finally this becomes less steeper, which indicates that this time the object's velocity or object's speed is now decreasing with time, right? Initially it is moving with higher speed, and finally it is moving with a lower speed. So this can again be expressed as decreasing speed as graph becomes less steeper with time. Okay, so this is your fourth graph done. And lastly for part E, this is again same concept. At every point the gradient of the graph would be same, but this time the distance is decreasing, right? So this is also a constant graph gradient or constant speed graph, but decreasing speed. The previous one was increasing distance, this one was increasing distance, and this one is for decreasing distance. So for part E also, this is still a constant speed graph. But decreasing distance. I'll just write D decreases, okay, in this arrow, that the value for your distance decreases over time. So these are the 5 shapes for your distance time graph that are very important for your exams tomorrow. I hope this section is entirely clear. Other than that, if you move on to your velocity time graph now, over here for your velocity time graph, they have also similar cases. Now in this section, this is a positive negative axis graph, because this is a vector quantity graph, right? Vector quantities can be positive and negative. So this is a positive or negative axis graph. Another thing to understand over here, for example, graph A in this case actually indicates constant velocity. Why? Because now the velocity is magnitude is same, but over time, I mean on this section we can see time is increasing, right? So point A indicates this is a constant velocity graph. This one, part B, indicates that object is moving with constant acceleration. Gradient for your velocity time graph gives you acceleration. Okay, so part B is now constant acceleration. And then again, obviously A would have a higher acceleration than B, right? So object A has higher acceleration than B because of the same reason that object A has a graph that is more steeper than object B. And lastly, for point C and D, it is what? Less steeper, more steeper. So over here for point C, for graph C, the object is no longer moving with constant acceleration but with a increasing acceleration, right? In this part it has a low acceleration, in this section it has a high acceleration. So for part C, increasing acceleration, for part D, it is more steeper initially and less steeper finally. So for that case, this is decreasing acceleration. This is still acceleration, by the way, but at a decreasing rate. This is not deceleration, this is decreasing acceleration. That means with time the value of your magnitude of your acceleration decreases. Previously it was moving with 10, then 5, then 6, similar to that. Okay, the magnitude of your acceleration decreases but is still positive. It is not deceleration. And point E over here, this one is deceleration, and that too at a constant rate, right? We can see this is a what? Constant straight slant line, so gradient will be same, but this is a down sloping graph. For down sloping graph for down sloping graph, the entire magnitude changes. So previously for upsloping, if the magnitude was positive A, this time it will be negative A, and negative A indicates this is deceleration, right? So this is for constant deceleration. Okay, after this, these are the shapes of graphs that you need to understand very clearly for your distance time graph and velocity time graph. Other than that, we're going to understand now gradient calculations for straight line, gradient calculation for curved line, and the area under the graph. Wait, let me see if I have much space over here. I actually want to explain one more thing. Okay, so as I was saying that let's just identify, even though I didn't discuss about speed time graph or acceleration time graph or displacement time graph, but we still need to know what are the things that you're going to get under the area under the graph, or velocity or gradient for these type of graphs. For example, for gradient calculation, okay, we always do one thing. For gradient calculation, you always divide the y-axis over x-axis. Okay, this is the formula for the gradient calculation. And for area, I mean, doesn't matter whatever the shape is, area, for area calculation, at the end you always multiply the x-axis and y-axis. So for this kind, let's just identify the types of graph. Okay, types. Over here, let's start with distance time graph. Distance time. Okay, now for distance time graph, for your gradient over here, I obviously understand that this is going to be this is going to be your speed, right? But why does this give you speed? That's because distance over time, according to your calculation for gradient, distance over time is your gradient calculation, which obviously will give you speed. So that means from this graph over here, you are going to get speed as the gradient. And if you want to calculate the area, that is distance multiplied with time, this will not give you anything. Similarly, for the next type of graph, that is displacement time graph. Displacement time graph. For displacement time graph, again, if you want to find out the value for or whatever quantity you're supposed to get on your gradient, that is displacement divided by time. This one will give you velocity this time, and area will not give you anything. Displacement multiplied with time doesn't give you anything. And then again for your next type of graph, that is speed time graph. For speed time graph, again, if you want to calculate the gradient, speed over time doesn't give you anything, but speed into time, this time now you will get the distance. And then for your velocity time graph, that is your displacement. For gradient over here is going to be velocity by time. Velocity is by time is actually acceleration. So this one gives you acceleration. And for your area under the graph, this one should give you displacement. So this one should be displacement. Lastly, for your acceleration time graph, this one for the gradient calculation, if you remember, for gradient calculation it was acceleration over time. This one now that gives you nothing for the gradient, but this one for area will give you velocity. This is a very important chart that I have drawn over here, and it's extremely important to understand that what are the things you're going to get under the area, under the gradient, for which type of graph. So very important. I would suggest memorize this entire chart and understand every basic as much as you can. Okay, so this is a very important graph. I will list down the type of things we wrote. This is 1, 2, 3, 4 and 5. And again, this gradient and area calculations was also important. This was for the gradient calculation and this was for the area calculation. Okay, now after this again we used two equations over here. The equations were v is equals to dt, like the derivations of this, and the one equation was a is equals to v, basically change in v over t, right? These two equations are used over here also. Okay, yeah. Okay, now let's move on to your calculations for gradient and acceleration. So for example, over here, for example, if your graph is a straight line, right, then it makes your gradient calculation extremely easy. So this is a graph with a straight line only. It doesn't have to be an upsloping straight line, any kind of straight line, right? This is extremely easier to calculate the gradient from this part. For example, I will take any 2 points randomly from the graph, and I will take this is as x1, x coordinate for first point, this becomes y1, y coordinate for second point, this is x2, and this is what, y2 for the second point, right? For this kind of graph, for a straight line graph, the equation for a gradient is very easy. That is change in y-axis over change in x-axis, which is going to be y2 minus y1 divided by x2 minus x1. Right, you can easily use this equation, apply this equation on your graph, and that will give you the gradient for that graph specifically. So this equation is only applicable for straight line graph. Okay, and then again there's also tangent graph that you have to understand. For example, if your graph is not a straight line this time, it has a changing gradient. For example, this point, this shape of a graph, how can you find out the gradient for this type of graph? Then what you have to do is that you have to draw a tangent across one point. And always remember, if you guys have maths, it would make this type of calculations very easily. Any maths is applicable. For example, the maths B, maths A, pure maths, right? Over here, this tangent is actually going to give you the value for your gradient for this specific point, because always remember, tangent meets with the curve at only one point. Tangent does not meet with the curve at multiple points. Tangent will only meet with the curve at one point. So what will you do over here is that you will create a triangle with this tangent. You will create a triangle like this with this tangent. Okay, like this way, and now you can use this coordinates to find out the values for your y2 minus y1, x2 minus x1. For example, this one will be at y1, okay, and this point is at x1, this point is at x2, and then again this point will be at y2. I just have to extend this line a little bit, right? And now using your basics, now using the same equation, as tangent at the end of the day is a straight line, so now you can write gradient is equals to y2 minus y1 divided by x2 minus x1, right? Now using the concepts of gradient, now you can easily use that. So always for a changing gradient, for a curving graph, that is a non-straight graph, you have to draw a tangent. Over here, this is your tangent. Let me labelize. This is your tangent. And this kind of tangent has to be drawn for curved shapes graph. Curved graph, okay. And then again, these were the area, the calculations for your gradient. Other than gradient, there are area under the graph you have to calculate. Usually, the area under the graph is in the shape of these three sections, these three objects. Either it can be rectangle or a square sometimes, a trapezium or a triangle. Now, for this rectangle, this is your what? Length, and this portion is your breadth. And I'll write breadth over here. This is your breadth. For the area for this rectangle, this is going to be length into breadth, right? If it was square, then it would have been length into length, or length square, right? And then this is a trapezium. For trapezium, AB and your DC is actually parallel. These parallel to lengths are known as small a and small b, as you can see over here also, small a and small b. And in between these parallel lines, there should be a perpendicular height, right? This H over here, this should be perpendicular to the parallel line, so which will make this the height of the entire trapezium. So now for the area for this trapezium is going to be half multiplied with the summation of parallel lines multiplied with height, and this will give you the area calculations for your trapezium. Okay, understand the equations or memorize the equation for trapezium area is very important. And then again, this is a right angle triangle. Obviously, it is making 90 degree, which makes this the height of the triangle, and this portion the base of the triangle, which means over here the area for a right angle triangle is going to be half multiplied with base into height. Then again, very important to understand these three formulas or memorize these three formulas: area under rectangle, area under trapezium, and area under your right angled triangle, right? These are the usual area shapes that will come across in your exam paper. So yeah, this is it for all the things we actually need to know from our chapter 1. What are the basics of kinematics, what are the uses of, like, what are the things that kinematics has, assumptions and graphs, area under the graph, gradient of the graph, tangent drawing, and then we also listed down like what are the things you're supposed to get from which sections of the graph, right? Right, okay, then other than that, we have a question over here. We'll solve this question just so that we understand that we got the basics over here clearly. Now over here, this is a quick question. For this quick question, it says this is actually question 5 from a recent question paper. So this is just the question number over here. It doesn't indicate anything with the question. It's not involved with the question. Okay, it says that a driver and a car sees an obstacle at the road ahead and must stop the car. State the formula linking average speed, distance traveled, and time taken. Oh wait, sorry. Then traveled actually has the spelling double L, right? My bad. Now over here, always I already understand the equation should be what? Speed equals to distance over time. But always use the terms that are used in the questions. In the question, they used average speed. You have to use average speed in your answer. Then you cannot just write speed. Okay, so you have to use average speed is equals to distance traveled divided by time taken, right? This is your equation. After this again, it says that a car travels at 21 meters per second. The driver's reaction time is 0.04 seconds. Calculate the distance traveled by the car during this driver's reaction. Over here, the assumption is that object was moving with constant velocity. And from the very start, I know the equation for your constant velocity is v is equals to d by t. So in that case, v is equals to 21. I would always suggest, write the equation in symbols at least. D by t and then 21 over 0.14 seconds. Wait, I don't have my calculator. 1 minute. 21 0.14. This one turns out to be 150. Oh wait, 1 minute. They were asking about distance, all right? So I should have rearranged the equation. Vt That's 21 multiplied with 0.14. So that is 21 multiplied with 0.14. So within this 0.14 seconds, the object would have moved this much meter. But then again, I would not actually write my answer in 3 significant figures. Why is that? Because in your question, the data that they provided in 21 and 14 was in at least 2 significant figures, right? As they were in 2 significant figures, I should keep my answer in either 2.9 meter or 3.0 meter. But I cannot keep my answer at a greater significant figures than the SF used in the question. That is because higher the significant figures, higher the accuracy of your data indicates. And your answer should not be more accurate than your data provided by the question. I hope that concept is clear. Then again, the car experiences a braking force of 7600 Newton and the mass of the car was this much. Linking formula, mass and acceleration. Even though we didn't revise this part, but we can solve this, right? This is going to be what? Force, mass times acceleration. After this, then calculate the acceleration of the car. Okay, we can clearly understand that. We can clearly calculate that. This is going to be F divided by A, which was 7600 over mass was I think 1200, right? Yeah. 1200, so which is 7600 divided by 1200. This one turns out to be 6.33 or 6.3 meters per second square. The unit for acceleration is meter per second square. Okay, this is it for your question. Now let's quickly move on to your concepts about forces and shape. Okay, now for forces and shape, this is again an important definition, that this is the push or pull that changes the shape or direction of the motion of an object. Why the direction of the motion of an object? That is because it will always move, like the object will always move in the direction of the resultant force, right? So that is the case. This is a very important definition for your exams tomorrow. And then obviously this equation F equals to ma, where force represents F and m is mass and a is acceleration. Over here it's quite important to understand the unit for force is not actually in terms of the units used in the question. This is actually named after the scientist Isaac Newton. So your value or your unit for force is actually capital N, representing newtons. And according to your equation for mass and acceleration, product of mass and acceleration should give you kg meter per second square. That means this one turns out to be your SI unit, okay, named after the scientist, and this one turns out to be your base unit, basically derived from all the quantities that were used in the question. So quite important to understand that what Newton is in terms of base unit. They might ask you this also in a question paper. And other than that, this is obviously a vector quantity. If you can carry out your dot multiplication we learned in the previous section to identify if force is actually a vector quantity or not. This is a vector quantity. Okay, yeah, this is it. And then again, it's quite important to understand mass also. This is the measurement of quantity of a matter in kg. Unit should always be in kg, right? And then weight, it is the gravitational force of an object. This is an important definition, right? Gravitational force on an object. Now again over here, the weight is equals to mg is actually a derivation of F equals to ma also, because weight itself is a force, mass is mass, and this g is the value for your gravitational field strength, by the way. Some people think that this is gravitational acceleration, but no, this is gravitational field strength. This is weight, mass multiplied with gravitational field strength. Some people, most of the people actually get confused for these two values for g. One is for gravitational acceleration, one is for gravitational field strength. At the end of the day, both have same value, that is 10 over here. For example, gravitational field strength, let me identify the difference over here for gravitational field strength and for gravitational acceleration. Okay, gravitational field strength and gravitational acceleration, right? That is what we are trying to understand. 1 minute. acceleration and gravitational field strength. Now over here, gravitational acceleration is the constant acceleration under gravitational force, and gravitational field strength indicates that how strong the gravitational field is across a mass. So in this case, the value for G is still 10, and again over here the value for G is 10, but only there is a difference in between the unit. For acceleration, the unit is meters per second square, and field strength, this is Newton per kg. Okay, that is the difference between the gravitational field strength and between your gravitational acceleration. I hope this is clear, the difference between gravitational field strength and gravitational acceleration. Now after this, again we'll move on. We have another type of force to understand, that is friction, that opposes motion, and obviously it is higher for rough surfaces and smaller for smooth surfaces. Okay, let me just write this down. Higher for rough surfaces. Now again after this, there are 3 Newton's law, which is again extremely important. Obviously they will not ask you to memorize this, but this is important to understand, important for your basics. For example, Newton's first law, what this indicates? This indicates that it states that an object has a constant velocity unless acted upon a resultant force. Constant velocity over here, this indicates that an object will remain to move at a constant velocity, or will remain to would like to remain at rest or stationary unless or until there is an external force acting on that object. So this one is about inertia. The higher the mass, higher the force that has to be provided for that object to be moved, for object to change its state. So over here, this indicates that constant velocity is a resultant, is a mark scheme point, and this one is a mark scheme point. Other than that, Newton's second law, it states that force is directly proportional to mass in acceleration. F equals to ma, that is your Newton's second law. And then again after that, Newton's third law, that every action has an equal and opposite reaction, right? So every action has an equal and opposite reaction. So these are the 3 Newton's law, which is again extremely important to understand. So we'll move on. Then this is about shape. Shape contains Hooke's law. We obviously have to memorize Hooke's law. We obviously have to memorize definitions about elastic limit and limit of proportionality. Now over here, and also understand the shape of this graph. Over here, Hooke's law states that, okay, so in Hooke's law, it states that extension is directly proportional to your force applied. Okay, this is extremely important, this line, that extension is directly proportional to your force applied. Over from this line, you can actually no, that equation is not related to your IGCSEs. No, sorry, no need to understand any relationships. Now over here, we just have to memorize these lines, that extension directly proportional to your force applied. And then again, there's also an addition limit. For this part, you will actually get 1 marks, and for the rest of the part, you will get the other marks. Okay, so this is a 2 mark questions again. Now then they says that provided its limit of proportionality or elastic limit is not exceeded. This entire statement over here is there for your 2 marks. So I would suggest obviously memorize this entirely from tip to toe to get that 2 marks. Now again, this is a graph. From this graph, this is going to be a limit of proportionality. Now how can you understand this is going to be up to this point is going to be a limit of proportionality? Because limit of proportionality is up to the point for which force and extension graph is straight line. So what you're supposed to do over here is you're going to take a scale and start drawing a straight line. You can clearly see that the line is straight only up to that highlighted section, right? After that point, the line, the graph starts to curve down, and this black line turns out to be straight, even that section also. So this is the point after which your force extension graph will start to curve down, and up to this point your graph over here is a straight line, which means now for this point on this graph, this point is your limit of proportionality. So I will just remove this then, and yes, this is your limit of proportionality, and exactly after limit of proportionality is your elastic limit, and this is the final force that the spring can take before it will break down. On your y-axis, this time you will have force, and x-axis you will have extension, and then again over here, elastic limit, very important definition again. Object changes shape temporarily before this limit, and after this limit object changes shape permanently. So object changes shape temporarily up to elastic limit. I should have referred that over here, that this is up to elastic limit. Elastic limit. There's also one equation that is related to this case, that is only how to find out extension. For example, over here, if I take this type of diagram again, original length of a spring is this much, okay, and when you applied the spring, like when you applied a force of mg Newton, okay, a force of mg newtons on this spring, the spring obviously extended. Now you can clearly understand this was the original length and this is the extended length, right? In order to find out the extension over here, this is the length 1, original length, and this is your length 2, extended length. In order to find out the delta x, this is your delta x. In order to find out extension, that is going to be new length or extended length minus original length, which in symbols can be represented as delta x. Delta obviously represents change in that quantity, and this is going to be L2 minus L1, right? Very important question over here, very important equation for this section of the chapter, forces and shape using Hooke's law. Other than that, we have elastic limit, elastic force extension graph for rubber band, which is again quite important. For this rubber band over here, in this case, this is for uploading. Sorry, this section, the upper line over here, this is for uploading, when you're going to add forces to that graph, to that rubber band, okay. This is for uploading and this is for downloading. I mean, downloading over here, not exactly downloading files from internet, but downloading means when you are like, you know, not exactly downloading, should be the proper word should be unloading, right? Yeah, sorry, I was not getting that word in my mind. This is unloading, right? So that is uploading and unloading, and within this two graphs, right, this area over here will represent the energy lost during the uploading and downloading. Obviously, in elastic rubber bands, right, in rubber bands they have this elastic energy stored. Because of this elastic energy stored, you know, they can go back to their original shape. But problem is, if the elastic energy is used during this uploading and unloading, the object will not or never return to its original shape. That is what happens over here for rubber bands. In rubber bands, as you can see, this is the shape for your uploading and this is the shape for your unloading. They are not same. That is because some of the energy, elastic stored energy, was lost during these cases. So there's one condition over here: if object can return to its original shape, or if an object can change its shape temporarily, temporary shape change indicates that over here the object's elastic stored energy was conserved, right? It was not lost. So elastic energy is conserved, and if an object changes its shapes permanently, this indicates that elastic stored energy is lost. It was not conserved, this time it got lost to the surroundings. So these are again two very important points for your sections over here. Right. Other than this, there's nothing else for Hooke's law. We'll move on. This is about thinking distance. I think from this part we are starting the chapter 3. For this thinking distance over here, this is these are the definitions that will have to memorize for your cases when the car is about to brake, when the car sees an obstacle, or other these kind of changes that might come across along the road. So for this case, for thinking distance, first one over here, for thinking distance, this indicates that the distance the car traveled during the driver's reaction time. And then again for the stopping distance, this is the total distance, the total distance traveled during the thinking time and braking time. While the car is braking, while the driver is still thinking, right, within that time also the object actually travels certain distance. Okay, always remember that within this thinking time, object moves with constant velocity. So object moves with constant velocity. That means for your thinking distance section, you should use the equation v is equals to d by t to calculate the time or distance or whatever you need. And for your braking distance section, 1 minute. Object is actually decelerating. Object decelerates. Sorry, made a mistake. Wait 1 minute. There has to be one e in between. Okay, object decelerates. So over here, your equation should be v is equals to a minus a is equals to v minus u over t. This is the equation that you are supposed to use for this section of the journey. Now again, we can see over here, in this section you can see in which portion the object was moving with thinking distance and your braking distance. For example, over here, if your object was moving with 30 meters per second, it travels a very smaller thinking distance, a smaller braking distance, right? But when your object was traveling at 50 meters per second, the braking distance increases. This 70 meters per second, braking distance also increases. That means the initial velocity with which the car was moving only affects the braking distance. The thinking distance obviously increases, but that is entirely because of the driver's fault. Thinking distance increases if the driver is affected somehow. If the driver has consumed alcohol, if the driver has poor vision, if the driver has large reaction time, or if the driver is sleepy, right? These are the points that will increase your thinking distance. And for braking distance, we can see that initial velocity is a very important point. Initial velocity and road conditions will obviously hamper your braking distance. So again, I should include a chart over here for what are the things which are responsible for thinking distance and braking distance. Okay, so we will write thinking distance on this portion. Sorry. And braking distance. Now this is again very important. These 3 points come very often in your exams. So the first point over here for thinking distance is if the driver is tired, then another point could be that driver is sleepy. And then again lastly, consumed alcohol, or poor vision. Okay, these are the 4 points for increasing thinking distance. And for increasing braking distance, they could be weight, like road conditions, wet road, oily road, right? They will increase this will cause the car to slide, and if the car is going to slide, then obviously they will travel a larger distance. So wet or oily roads. And then again, tire conditions also causes an increase in braking distance. Worn out tires or old tires. And worn out tires is a basic mark scheme point, so I should use worn out tires better. And then again, high initial speed. This one, high initial speed. And lastly, what else? Oily road, worn out tires, high initial speed. Yeah, these are things actually, nothing other than that. This is again a very important thing, factors that would increase your thinking distance and braking distance. I would suggest memorize this entire chart over here. Okay, other than this, there's actually a graph over here that you should understand. Let's understand this graph. We can clearly understand one thing over here. Objects moves with constant acceleration for your for your thinking distance. So this is your thinking distance. Let me highlight this again. This portion is entirely your thinking distance. Okay, when your object is moving with constant acceleration, constant velocity, sorry, and this portion is for braking distance. When your object is decelerating, that is for braking distance. This portion is for braking distance. 1 minute. Okay, this is for TD, thinking distance. This is for BD, braking distance. Okay, now over here we can see that initial velocity was 24 and it was only the reaction time over here was what, 0.75 seconds. From that 0.75 seconds to almost 3.25 seconds, within this time duration the object was braking. Now it says that how long the driver takes to react to see the obstacle, basically the reaction time, which we know 0.75 from the graph. So this is 0.75 seconds. Then again, how far the car travels during this reaction time, that is basically area under the graph, because velocity time graph gives you the value for its distance. So this is area under the graph, which would be 24 multiplied with that 0.75. So that's 24 0.75. This is going to be 24 0.75, that is 18 meter. Okay. After this, how long it takes to bring the car to halt once the driver starts braking. For the total time, how long after braking, so no total time, this is the braking time, that is what, between 3.25 to 0.75. You just have to subtract 0.75 from 3.25. So if you do that, you are going to get 2.5 seconds. So this is 2.5 seconds. And then again the total distance is basically this purple line and this blue sections. For the purple section, I already know it was 18 meter. For the blue section, this is what, triangle, half into height is 24 and base is that 2.5, right? So this is 0.5 multiplied with 24 with 2.5. This is going to give you 30. Eventually total distance is going to be 18 and 30. 18 plus 30, which is 48 meters, right? And that is it, the calculation for your area under the graph for a thinking distance, braking distance concept. After this is your case for terminal velocity. Now then again, terminal velocity is actually a fancy word for constant velocity, but in fluid medium. Fluid indicates both the medium, in gas and in liquid. Okay, so for example, on ground you would use the term constant velocity. On air, in air you would use the term terminal velocity, and again in fluid or in liquid you would again use terminal velocity. So this is our entire concept about terminal velocity. Now over here what happens is that initially, this is like 3 sections for your terminal velocity, very important. Initially this is your scenario 1, where only the weight acts downward. Okay, only because of this point, when your weight is acting downward, object is accelerating at the maximum rate. Okay, so at this point at scenario 1, the acceleration is your 10 meters per second square, the maximum acceleration. But with time what happens, obviously as your object is accelerating, as we have already started in the first section of this video, that as your object is accelerating, its velocity will also increase, right? So as due to its velocity increases, now over here in scenario 2, as velocity increases, velocity and air resistance is also like directly proportional. So air resistance, AR represents air resistance, this also increases. And obviously air resistance is a reversive force, is a resistive force. If air resistance increases, this overall decreases your total resultant force. And again, if resultant force decreases, the value for your weight, not weight exactly, if resultant force decreases, according to your equation F equals to ma, mass is constant over here, right? So if force decreases, acceleration should also decrease. So with time what happens, initially it has a higher acceleration, but with time acceleration's rate would decrease, and acceleration would eventually be entirely zero when this, at the third section, when this drag force or air resistance becomes equals to the weight. At this point resultant force becomes 0 and acceleration becomes 0. We have studied so far that objects acceleration can be 0 in two different situations. If the object is moving with constant velocity, if the object is not moving at all. Over here the object was moving with constant velocity. So this is your first terminal velocity reached, V term reached over here. This is the scenario when your object is going to reach the first terminal velocity. After that, what happens when the parachutist or skydiver will open a parachute, right? Opening a parachute increases the surface area. That means all of a sudden air resistance extremely increases. So at scenario 4, this is not drawn over here, but on scenario 4, what happens? Parachute opens, right? When your parachute opens, I'll just write this down over here. When parachute opens, the weight or drag force, air resistance becomes extremely greater than weight, and now object starts to decelerate. Okay, the object over here doesn't start to move in the opposite direction. The object starts to decelerate in this section, and when the object is decelerating, velocity will again decrease. As soon as velocity decreases, air resistance also will try to decrease over time. And then again at the final fifth position, air resistance again become equals to weight, where eventually the value for your acceleration turns out to be 0, reaching out your second terminal velocity. Okay, now just give me 1 minute. I'll obviously summarize all of these things into one file and then explain these things in much more detail. Let me just find some space. Problem is I didn't actually kept much space over here. Okay, so I had to scroll all the way back to get some space. I was trying to explain the 5 scenarios for terminal velocity, right? So this is for let me just write a heading over here. Okay, this is for terminal velocity. Okay, now terminal velocity over here in the first scenario, what happens is only weight acts downward, right? So only weight acts downward. Because of this weight, RF is equals to weight. That means A would be equals to gravitational acceleration, that's 10 meter per second square. So this time it has the maximum acceleration. Okay, but then we move on to section 2 now, scenario 2 now. In scenario 2 again, what happens? In scenario 2, the value for your velocity also increases, right? As object is accelerating, I should write as object, 1 minute, accelerates, velocity also increases. Okay, now with this increase in velocity and air resistance are actually directly proportional. So if velocity and air resistance are directly proportional, velocity increases, then air resistance must also increase. And because of this increase in air resistance, this is a resistive force, right? So overall resultant force decreases. And again, if resultant force decreases, acceleration would decrease. So now object is now increasing, like moving downwards in a lower rate of acceleration. Then comes your scenario 3. In scenario 3, what happens? Obviously, your object acceleration was decreasing. Because of decrease in acceleration, velocity will also decrease. And again, because of decrease in velocity, as again air resistance was directly proportional to your wait 1 minute, object's rate of acceleration was decreasing, right? But velocity will keep on increasing because it was still not decelerating, it was still accelerating, right? Maybe the rate of acceleration is decreasing, but it is still accelerating. So for this case, velocity increases. If velocity keep on increasing, air resistance will keep on increasing until or unless it becomes equals to your weight. And then this section again, resultant force again becomes 0. As there is no resultant force, all the downward force was cancelled out by the upward resultant force. Air resistance, acceleration is 0. So first terminal velocity is reached, V term. Okay, and then comes your scenario 4. In scenario 4, what happens? Now object over here, what happens is that the parachutists open the parachute. So parachute opens. So if your parachute opens, in this case, all of a sudden surface area is also again directly proportional to air resistance. When parachute opens, surface area increases, air resistance increases. This time now air resistance is extremely bigger than weight. So there is a resultant force but in the upward direction, right? This in a resultant force in upward direction, and because of this resultant force in upward direction, object starts to decelerate. Because of the deceleration, what happens? Velocity again drop down, right? And if velocity drops down, object's air resistance would again drop down. So this is your scenario 5, start of scenario 5, which is going to be due to deceleration, velocity drops down, and then due to deceleration, like velocity drop down, acceleration would also drop down. If acceleration dropped down, the value of your air resistance drop down. If the value of your air resistance will continue to drop down until or unless it becomes equals to weight again, where then again all of the resultant force is 0 and your second terminal velocity is reached. Right, this is the entire scenario for your terminal velocity, all the 5 cases that is happening over here. So I would suggest memorize all these things, whatever you need to do this with this chart, extremely important. Okay, then we'll move on to your case. I didn't have space over there, so I had to scroll down all the way back to include some space. Now over here we need to understand what is happening for all the shapes over here, for all the sections A, B, C, D, E. So we will write that. For example, at point A, the object is the parachute falls off the plane and it is accelerating at the maximum rate, right? So falls off, max acceleration. Okay, and then again at B, the value of your acceleration now starts to decrease because of air resistance. So A starts to decrease due to air resistance. AR obviously represents air resistance. I hope that's clear. I'm sorry I don't have much space over here. And then again at point C, this is your first terminal velocity when weight and air resistance is equal. So this is AR equal to weight, that is your first V term. Okay, and then at point D, the parachutist opens the parachute. So for point D, wait, I think I should write these things at the very base, because it really doesn't have space to write all the sections over here. Or wait, can I get some space in this section? 1 minute. Yeah, I'll just start writing the labels over here. For A, falls off, max acceleration. For B, acceleration decreases as air resistance is present. At point C, first V term. Now I am using V term because of my space problem, but you have to write terminal velocity. They will not give you any mark with writing V term. And this is the case when air resistance is equals to weight also. At point D, parachute opens. Okay, at point E, this is going to be your deceleration. As you can see, the graph becomes downward sloping, right? This is deceleration when air resistance now very much bigger than weight. And at point F, this is your second terminal velocity. I'll just write V term. Okay, that is the case when again air resistance again become equals to the weight of the object. So this is your entire scenario, 6 scenarios for your terminal velocity graph. This is an extremely important graph. I would suggest memorize this graph, different sections for this graph. Okay, other than this, there's nothing else. We'll move on to your next topic. I think that is the end for your kinematics and motion. We'll now move on to your moment concept. Right, this is it. Other than that, nothing else is important. We'll now move on to your moment concept. Okay, now for moment over here, in this is a definition for moment, quite important, that it is a product of force and perpendicular distance. Always remember, the distance always has to be perpendicular to the direction of force. For example, in figure 1 over here, as you can see, it is quite easy, right? This is your pivot point. Pivot point is a point through which the object will rotate. Moment is also known as the turning effect of force, right? We are going to provide a force on an object, and the object this time will not change its position. It will just rotate about a fixed point, and that fixed point is known as pivot. So now over here we are applying a force in this direction. So in this case, from the pivot to the force, the distance has to be perpendicular. Right? This is the value for D that you are going to take. For moment is actually described as, or a symbol of capital M, and moment is basically force into this distance. Now over here moment is a vector quantity, so directions over here is quite very important to understand. This is a vector quantity. This is a vector quantity, and this unit over here is Newton meter, right? Because force is measured in newtons, distance is measured in meter. And then again in figure 2, if you see, this one is quite different, because this time you're not providing force perpendicular to the other side of the spanner. Right? Now you are providing force in an angular way to the spanner, but this time in order to find out the distance, perpendicular distance from force to pivot, this is the perpendicular distance from force to pivot. So this is the value for D that you are going to take in your calculation. So always remember, you have to measure the distance from force to the pivot, and the distance has to be perpendicular to your force, okay, direction of your force. And this is it. Now we have discussed the Newton meter unit, and yeah, that is it. Okay, now again the law of conservation of moment, very very important. Again, law of conservation of moment, it is a very repetitive definition that might come across in your exam paper. So quite important, remember and understand this also. For law of conservation of momentum, it says that sum of clockwise moment is equals to sum of anti-clockwise moment. Now from this understanding, let's just understand what is clockwise moment and anti-clockwise moment. This is how you will refer to clockwise and anti-clockwise. This is a entire beam, okay, and I'm going to make this beam in this direction. Oh wait, 1 minute. Okay, I'm going to make this beam move in this direction, right? This is what, about this fixed point, it is just moving in this direction. This is clockwise direction, the direction which your clock rotates, right? And if it was rotating in the opposite direction, in this direction, this is the anti-clockwise movement. This is clockwise and this is anti-clockwise. Okay, I'm not sure if this is correct or more confusing, but if your beam moves in this direction about the fixed point, then this is your clockwise direction, clockwise direction. And if your beam moves in this direction, that will be your anti-clockwise direction. Quite very important to understand. Now over here, you can actually express an object to be in equilibrium in two different statements, either writing in terms of force or writing in terms of moment. An object in equilibrium means that there are multiple forces acting on the object, but at the end of the day, the object is at a balanced position. Okay, the object will not have any resultant force in that case. So equilibrium can be expressed into two different definitions. We'll express that again a little bit later, but let's just first understand what moment over here indicates. For example, in this case, we can see that this is your pivot, right? There's actually forces of 15 Newton, 15 Newton, 15 Newton, 10 Newton and 25 Newton acting, right? And in your calculations over here, what this indicates is, like, this is just a explanation for clockwise and anti-clockwise, okay? This is not a maths, this is a maths over here. Example 1. In this case, always in the law of conservation of moment, there will be certain thing missing, either force is missing or distance is missing. For example, over here there is this force that is missing over here, and you need to find out the value for this force. How can you find this out? For example, label down what are the forces acting in the clockwise direction. For example, these two forces will act in the clockwise direction and these two forces will act in the anti-clockwise direction. So according to this basics, according to your law of conservation of momentum also, you will write this equation like this, that clockwise moment is equals to anti-clockwise moment. This law of conservation of momentum indicates the object will be at equilibrium. That means at the end of the day, all of the upward forces should be equal to the downward forces, okay? This indicates object is at equilibrium. That is basically, now you have in the clockwise forces, what is this? 20 into this distance, right, which is 1.5. You always have to measure the distance from the force to the pivot. This is your pivot. So you have to find out the distance from that force to this particular distance. For example, this force, this is going to be 1.2 plus 2.5, right? Both of the forces distances will be added over here. So this one will be 1.2 plus 2.5. This turns out to be 3.7 plus F 3.7. And then again in anti-clockwise direction, you have 50 multiplied with this one would be what? 2.5, right? So 2.5 plus 100 Newton multiplied with 1.2. From this cases, now you get 20 into 1.5 is 30 Newton. This is going to be 3.7 F. 50 multiplied with 2.5 gives you 125, and 100 into 1.2 gives you 120. Yeah, 120. So you just have to make that F subject of this equation. That will be 125, 120 minus 30 divided by 3.7. So 125 plus 120 minus 30 divided by 3.7, which turns out to be 58.11 Newton approximately, right? So this is the value for your force. This is how you're going to use the law of conservation of momentum. And then again, as I've stated, that I wanted to explain one thing about equilibrium. I'll write that down over here now. Yeah, after that we'll start momentum. Okay, so this is the two kind of statements which is required for equilibrium concept, that if object in terms of forces, if an object is in equilibrium, that means resultant force is 0 and the object is at balanced position. And in terms of momentum, this should be sum of clockwise moment equals to sum of anti-clockwise moment. This is again extremely important to memorize the two different definitions for equilibrium in terms of force and in terms of moment. Okay, that is it for moment. We'll move on to momentum then. Okay, now in this case for momentum, over here for momentum it says that this is the product of mass and velocity. Again, from this statement I can understand the equation, right? This is your equation for momentum, as we can see, mass and velocity. And from this equation also we can understand to write this in terms of symbols. For example, momentum is actually, unless moment, we cannot use capital M to express momentum. Over here we have to express momentum as capital P, mass and velocity. Okay, and in this case also momentum is a vector quantity, which means direction is obviously going to be a very important factor over here. And lastly, the unit for momentum is kg meters per second. That means if the value for mass is not in terms of kg, you have to convert that into kg. If the value for mass is not in terms of, velocity is not in terms of meters per second, you have to convert that into meters per second. For that case, these are the few conversions which are needed. 1 kg is equals to 1000 gram, 1 meter is equals to 100 centimeters, right? I hope you guys are aware of the basic unitary method we have to use for physics. I'm not explaining that over here. So these are the conversions we have to use. And then again, 1 hour is actually equivalent to 3600 seconds. Okay, these are basic informations which are needed. Okay, so these are the basic conversion units. And after that, let me just highlight this once. Okay, after that we have again law of conservation of momentum. Again, a very important topic, so I would suggest memorize this one also. According to your law of conservation of momentum, now this says that total momentum before collision is equal to total momentum after collision. Just writing up to this will give you 1 mark. For an extra additional mark, you have to write this point, provided that no external forces acts on them. A very important 2 markers over here. Okay, and these are the types of collision that you can see. This is scenario 1. Scenario 1. In scenario 1 over here we can see this is for before collision, during collision, after collision. No, we are only interested about before and after collision. It was already stated in your law of conservation of momentum that momentum before collision, after collision was equal, right? Which this indicates is before collision is equivalent to after collision. Thus this one indicates that mass 1 initial velocity of 1 plus mass 2 initial velocity of 2. Problem is they were traveling in opposite direction, and over here momentum is a vector quantity, right? So I have to assign different signs in this case. So for this situation I'm taking direction towards right as positive, so this one will be negative. Now in this case, as after velocity object 2 was traveling in right, so this one becomes positive and this one becomes negative. So in that basis over here this one turns out to be negative u2, and then again m1 u1 would be v1 after velocity is v1 plus m2 v2, right? This is how the entire equation can be arranged. We can simplify this and write it as m1 u1 minus m2 u2, and then again minus m1 u1 v1, final velocity is v1 plus m2 v2, right? This is one of the equation arrangement for scenario 1. For scenario 2 over here, this is your scenario 2. For scenario 2 in this case, we can see that object 1 and 2 are moving in the same direction, and again after collision they would still travel in the same direction. Over here in this part, equation would be before collision, after collision, similar process. Now in this situation also, obviously as long as we are working with collisions with momentum, direction importance plays a very important role, but over here everything was direction towards right, so was traveling towards right. So I'll just consider all of the things with the positive signs. In that case, now I have m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2, right? There will be no negative signs assigned because for this scenario everything was traveling towards the right. Nothing has its own direction over here. And for the last scenario, it was not drawn over here. I could not find any specific scenario for this in internet, so I have to draw this now. Just 1 minute. This is how maybe your diagram would look like. Okay, there is two balls, mass 1 and mass 2, and again after collision you have two balls, mass 1 and mass 2. But okay, in this situation what is happening is this is your before collision section and this is your after collision section. Okay, now before collision what happens is the objects were traveling towards each other, right? So I'll consider this one as positive, this one as negative, and after collision both of them are combined together and is traveling with a combined velocity, and this is again in the positive direction. So over here also I'll write that before collision is equals to after collision, and eventually what happens, before collision is now going to be m1 u1 plus m2, this is going to be minus u2 because it was traveling in the opposite direction, and then again you have this m1v plus m2v. Over here on the right hand side, if you focus, they were both traveling with the same velocity, right? So what I can do is that I can write m1 u1 minus m2 u2, and I can just take their mass 1 mass 2 common with the combined velocity. Right, this is again a unique scenario where after collision the masses will be combined together and start traveling in the same direction. So these are the three arrangement of equations which are important for your exams tomorrow. So I hope that this entire thing was quite helpful for the three different scenarios. Okay, this is it. This is it for momentum then. After this, there's nothing else from momentum. We'll now move on. This is actually the end for unit 1 topic entirely. So there's again a very small quick question that we're going to solve. It says that name a piece of equipment that he could use to measure weight. I mean, that is a what? Weighing machine or top pen balance, anything, right? So I'll just write top pen balance. Or you can also use weighing machine. Both are correct. Okay, then again state the equation linking weight, mass and g. So this is going to be what? Weight, mass, as they used g, so I'm just also going to use g. Calculate the mass of the cannonball. The weight over here was 50. So in that case, mass is going to be weight over g That's 50 over 10, which is just 5 kg. That is your final answer. Describe how the student could find the density of the cannonball. He should include the details of any further measurements he should take in to make. For example, this is a calculation for density of irregular object. So what I would suggest is that we'll keep this in a hold. We'll move on, and in the next sections exactly we will actually start with our density calculation or understanding. So we will skip it for the time being. I'll again come back later. Okay, so part C now. A cannonball is fired from a cannon. When the cannon is fired, the cannon moves to the opposite direction as shown in the diagram. This is the case. Use ideas about momentum. Explain why the cannon moves in the opposite direction. This is quite a very repetitive question, I would say. Now for this basic, why does this moves in opposite direction? That is because previously when the cannonball and your what is this? Cannon, right, were combined together, they were at rest. So both of them had a combined velocity of 0. But as soon as your cannon, pops out that cannonball out of it, cannonball now has a velocity, and then again it has a very smaller mass compared to the mass of this cannon, right? So in this case, if you remember, the initial velocity was 0 for this system. So in that case, initial momentum was also 0 before collision, and after collision, now as it has a velocity, right, this should also have a velocity. Problem is over here, mass is extremely small, mass is extremely large. Mass and velocity are actually inversely proportional. A larger object will have a smaller velocity, and a smaller object will have a larger velocity. Okay, so in that case, since over here the mass of the cannonball is very small, so it will move in the forward direction with a very large velocity, and because of this cannon has a very larger mass, it will move in the backward direction with a very small velocity. And that's why at the end, for example, I'll just consider random values over here. Okay, the mass of the cannonball is 1 kg, the mass of the cannon is like 20 kg, and previously they were both at rest. So this is how the equation for before collision momentum, momentum m not p, momentum would look like. So it will be what, 20 plus 1 multiplied with 0, that would be 0. And after collision, momentum would actually be your 20 multiplied with, I'm considering this will move with 20 meters per second and this will move with 1 meters per second. So this will be multiplied with 1, but then again they are moving in opposite directions. So what happens? This is positive, this is negative, this is positive, then again 1 into 20. At the end of the day, what happens? They both have equal momentum in opposite direction. So they will cancel each other out, and final momentum after collision also remains same. And if in this case, this obviously conserves your law of conservation of momentum, right? The total momentum before collision is equals to total momentum after collision. So we'll just write down the answer over here. No need to, I'll just keep this over here. Okay, that momentum before and after should be conserved. Should be conserved. That means total momentum after collision should also be 0. For that, they have equal momentum in opposite direction. Should also be 0. Equal momentum in opposite direction, so that they can cancel each other out, obviously. Opposite directions. Okay, now that is the end for your momentum concepts. We will now quickly move to energy, power and work done. I know in your book after this electricity starts, but I think kinematics is quite related to energy, power and work done. So in my regular classes of IGCSEs and IAL also, we always do these chapters simultaneously. or one after another. We'll first start with your kinematics and then move on to your work, energy and power. And then similarly, electromagnetism is related to your electricity. So we'll start electricity and electromagnetism together at the end part. So let's start with this work, power and energy. Definitions are quite important. Power, work done for energy transferred per unit time. From this statement also we can understand one equation, that is work done per unit time, right? So from this part we can understand that power is equals to work done over time, or it can also be broken down into energy over time. Another way we can express power, that is in terms of electricity. I know we're not in electricity, but I'll just write down all the derivations of power that I can think of at this point. That is, another equation is power is equals to IV, current into voltage, right? These are the equations, 3 equations for your power. Obviously have to remember the unit for power is actually joules. Sorry, my mistake. This is actually watt. Unit for power is watt, named after the scientist obviously. So this is watt, measured watt, capital W. And in this case, if you try to understand if this is a scalar or vector, you can use dot multiplication. Energy is a scalar, time is a scalar, so obviously product or division of 2 plus or positive sign will eventually give you 1 positive sign, which means this one is actually a scalar quantity. Power doesn't have any directions. Power is a scalar quantity. Sorry for this. Power is only a vector quantity. Power only has a magnitude, no direction. This is a scalar quantity. Other than that, we'll move on to kinematics. Kinetic energy. What happened? Okay. We'll move to kinetic energy. For this kinetic energy possessed by a moving object or by an object in motion. That means now the object must have velocity. So from this case also, we arise with the equation, that is Ke is equals to half mv square. And then we have gravitational potential energy, which is the energy possessed by an object which has height above the ground. So this is going to be GPE is equals to mgh, where m is mass, g is gravitational field strength, h is height above the ground obviously. And again over here, this statement is actually taken from your book example. This is very extremely good actually, in order to explain how kinetic energy or gravitational potential energy changes over time. Now in this case we can see that at the I'm just considering this as 0.1, 0.2, 0.3 and 0.4 when the object is exactly on ground. At 0.1 over here we can see it has the maximum height above the ground. So over here all the force is your gravitational potential energy. It has the maximum gravitational potential energy over here, and as it moves down, falls down, its velocity increases. If velocity increases, then obviously kinetic energy increases, and again as it moves down, its height decreases. So with time, as it moves down, because of decrease in height, gravitational potential energy decreases, and because of increase in velocity, kinetic energy increases. Another thing to important is your law of conservation of energy. Energy is not is not a thing that can be destroyed. It can only be transferred from one point to another point. So in this case, when your GPE was decreasing and KE was increasing, this was actually indicating that as the object falls down, all its GPE was converted to kinetic energy. So let me explain this to you, or write this to you again over here. From this part, as the object falls down, height decreases, as object falls down, height decreases. Due to decrease in height, GPE decreases, right? And as the object falls down, velocity increases. I'll just write increases, so your kinetic energy also increases, which means as the object falls down, all the gravitational potential energy gets converted to your kinetic energy. That's what we can see in this graph, right? As you can clearly see, this is your value for GPE. GPE decreases and kinetic energy increases. Very, very important section of your graph. You might be asked to explain this graph in your exam paper also, describe this graph in your exam paper also. So I would suggest understand the shape of the graph, understand how to describe the shape of the graph. and then again, sorry, 1 minute, and then again similar concept over here. In this case, at the very end, like over here, it has the maximum kinetic energy, right? But from this section to this point, as the object's height increases, velocity decreases. Over here, h increases, velocity decreases. That means in this section, in the upward section, what happens? Kinetic energy decreases and gravitational potential energy increases, right? At this very maximum point, it has the GPE max. And again, from this part to this part, this time height decreases, this is the opposite, and velocity increases. That means your kinetic energy again turns out to be max at this point at the bottom. Right, other than that, there's nothing. Okay, one relationship is between kinetic energy and gravitational potential energy. Okay, I'll just write this down over here. Now over here, obviously I can understand that your energy was not lost. That means over the time, the value of your kinetic energy should be equals to GPE. So in this case, half mv square is equals to mgh. Over here, both the m represents mass of the particle, so this gets cancelled out, and in that case we can write v square is actually what? 2gh, right? This is how you can actually find out the velocity. If you have the height above the ground, value for g is already known 10, you can just use this equation to find out the value for velocity, right? This is a very important derivation, again quite important, might arrive in your questions, so I would suggest highlight this also as your working process. Very important derivations. Okay, now we'll move on. This is for efficiency, very important. Efficiency can be expressed in terms of energy and power. So this is your equations for F energy, useful energy output, useful energy input multiplied with 100, then useful power output, total power input multiplied with 100, and then comes your pressure. Very important thing. Pressure is the force per unit area. In case for solid, it has the formula force over area, very simple. But if it is in case for liquid, then it has the formula height, density, and made a mistake, I'm really sorry. This is supposed to be height, density, and your gravitational field strength. Okay, rho gh, this is gravitational field strength. I actually didn't have time to go through this file once again to correct all these things, typing mistakes I did while I was compiling this PDF, because I had to do this like within 3 hours. I compiled this entire summary notes within 3 hours, so it was not quite possible for me to actually go through all of these things again and then correct my mistakes. Really sorry. This is rho gh. Okay, very important to identify the different equations for pressure in liquid and in solid, quite important. And then again, pressure over here is also a vector quantity. Okay, this is a vector quantity, that means obviously it has the entire magnitude and directions. Another thing, the unit is actually Newton per meter square, the SI base unit, but the SI unit is pascals, named after the scientist again. So this is your Newton per meter square, which is your base unit, and then again this is your pascals, PA, named after the scientist. Yeah, this is it. And again, one thing over here, efficiency calculations actually give you that how much efficient that particular mechanism or machine is. Okay, efficiency gives you idea that if how much of your total energy is actually being converted to useful cases. So efficiency says that how efficient that particular appliance is. So how efficient that appliance is. Okay, then after this we'll move on to the 3 states of matter. Again important, liquid, solid and gas. Not that much important to understand these, statements, melting, freezing, liquid, condensing. These are not important. These are important for chemistry, not in for physics. But this part is important. properties of solid, liquid and gas. They are rigid, not rigid, not rigid. They are fixed shape, they does not have fixed shape, they does not have fixed shape. Fixed volume, no fixed volume. High density, average to high density, then low density. Closely packed but not like that in solid, and then loosely packed. Then you have slightly compressible, highly compressible, right? Yeah, these are very important things. I would suggest go over these things, nothing much to explain because this is a revision video, right? Yeah, I'm not going to waste my time on these cases. I just included this so that you guys have an idea about all the things you need to remember. And again, as this file will be available for all of you, so I would suggest take this file from my WhatsApp or either from my Discord group so that you guys can revise from this. Okay, specific heat capacity, very important definition. This is the amount of energy required to increase the temperature of that substance by 1 degree Celsius, and it has the unit of joule per kg degree Celsius. This time the equation is delta theta. So delta Q, specific heat capacity, MC delta theta. Delta theta represents the change in temperature over here. This is the temperature, change in temperature. Okay, and this is an example taken from your question, like taken from your actual book, student book IGCSE 9 to 1. So let's just understand this to understand the concept of this specific heat capacity. I mean, from specific heat capacity, they will not ask you anything other than these normal maths. Other than maths, they will not ask you anything that much of descriptions or conclusions. Okay, only maths will be asked from this case. So for example, over here it was stated that if you fill a kettle of 300 gram of water whose initial temperature was 15 degrees Celsius, how much energy is needed to make that water heat up to the boiling? Obviously, we know boiling is what, 100, right? And specific heat capacity for your water is 4200. That means write down the things you know. Mass is 0.3 kg. Obviously, convert that mass from gram to kg. Very important. That mass should be in kg. Okay, and then specific heat capacity of water is 4200 joule per kg per degree Celsius, and the boiling temperature is 300. In that case, delta theta is basically what they subtracted this, right? Minus 15, which gives you 85 degrees Celsius. And one thing to remember, actually, difference in temperature in Kelvin and in degree Celsius actually is not different. Okay, so delta theta doesn't have to be its own degree Celsius. I mean, delta theta can be in Kelvin, can be in degree Celsius. That will not be a problem because delta theta, difference between temperature in the degree Celsius unit or in the Kelvin unit, is always same. Okay, and then again you just have to use this equation then, right? Mass is 0.3, 4200 and then 85, and that will give you 107,100 joules of energy that will be required for this specific heat, for this mass of water to increase its temperature for 1 degree Celsius. Yeah, this is it for specific heat capacity. After this, we'll move on again to the next part. These are for gas laws. Okay, for gas law over here, there are 3 laws: Boyle's law, Charles' law, and third law is not required for you, sorry. Yeah, Boyle's law over here. So Boyle's law indicates that at fixed temperature, the volume of gas is inversely proportional to the pressure of the pressure exerted by the gas. From this case, you can actually arrange this equation. P1 V1 is equals to P2 V2. Very, very important question. And again, over here there's one assumption, right? What was the assumption? The fixed temperature. This is your assumption, a very important case. In most of your questions, also in MCQs, they would ask you what was the assumption for Boyle's law. That is, the temperature has to be fixed. And then again, there's an example we can solve, that at atmospheric pressure of 100 kilopascal, obviously kilo stands for K. There are some prefixes that you should remember. Capital M stands for 10 to the power of 6, capital K stands for 10 to the power of 3, small m stands for 10 to the power of minus 3, then micro stands for 10 to the power of minus 6, nano n stands for 10 to the power of minus 9, and then pico, this stands for 10 to the power of minus 12. Quite new unit. Pico is very new. I think they asked this unit in somewhere of the recent question paper. I don't exactly remember, but this was asked. Okay, so these are some prefixes which are needed. Okay, then we'll move on. We were in this case. Now it says that some air is sealed in a container and has a volume of 2 meter cube at atmospheric pressure. This is the old pressure and old volume, right? P1, V1. What would be the pressure of the air if it was reduced to 0.2 meter cube? So we need to find out P2. So we'll write P2, V2, then P1, V1. We want to find out P2 because V2 is given, 0.2 meter cube is the volume. So it will be 2 into 100,000 divided by 0.2, and that will give you the value for your pressure. I'm so sorry I do not have my calculator, so just 1 minute. 2 multiplied with 1, 2, 3, 4, 5 divided by 0.2. 1, 2, 3, 4, 5, 6. This turns out to be 1, 2, 3, 4, 5, 6. We can write this as 1 megapascals, right? Because you have 6 zeros over here. So 6 means megapascals. Okay, that is the answer for this question. And then you have Charles' law. Charles' law is again important. This states that volume occupied by a fixed amount of gas is directly proportional to its absolute temperature if the pressure remains constant. Over here, the assumption is that the pressure over here has to remain constant. Wait, actually I made a mistake in this case. I'll write the equation now, that it's P1 T1 is equals to P2 T2. Right, over here directly proportional means that your value for pressure and temperature is going to be directly proportional only if, in this case, the volume is same. Fixed amount means volume must remain same in this case. Volume must remain same. This is your assumption this time for Charles' law. For pressure, for Boyle's law, the assumption was temperature must remain same. For Charles' law, volume must remain same. There are actually two assumptions. For this case also, mass remains same. That is another assumption for Boyle's law. And again for Charles' law, mass also remains same. So mass constant is a common point for both Charles' law and Boyle's law, and the other ones are different. Okay. So yeah, this is it for your Boyle's law and Charles' law. I would suggest memorize the formulas quite clearly. And then again over here, this is your absolute temperature. So in Charles' law, you cannot measure temperature in degrees Celsius. Temperature over here has to be in Kelvin. I'll obviously explain how to convert temperature from degrees Celsius to Kelvin right now, okay? But this is the very important case. In Charles' law, temperature always has to be in Kelvin. This is for your absolute temperature. For absolute temperature, we'll understand how to change your degree Celsius to Kelvin or Kelvin back to degree Celsius. This is an important, very important definition over here, that absolute temperature is the temperature measured by the Kelvin scale, where 0 is absolute 0. The 0 point is the temperature at which the particles of matter have the minimum motion and can become no cooler. Like this is the minimum energy that they can possess. After that, there will be no motion. I mean, and there is no point after that. This is a 0 Kelvin. This is the least temperature that you can provide to any particle. That is the least temperature over here. So the least temperature in Kelvin scale is 0 Kelvin, and in degree Celsius that is 273. So absolute temperature is actually zero Kelvin in Kelvin and minus 273 degrees Celsius in terms of degree Celsius unit. And okay, over here again, very important, in order to convert degree Celsius to Kelvin, you have to add 273, and again in order to convert degree Celsius to Kelvin, you have to subtract 273. That is extremely important for your exam tomorrow for both paper 1 and paper 2. And then again, this entire video is actually useful for both paper 1 and paper 2, because I'm explaining everything that will be included in both paper 1 and paper 2. Okay, nothing can be used just for paper 1 and paper 2. This is entirely important for both paper 1 and paper 2. Okay, this is it for absolute temperature. We'll now move on. This is for your density, extremely important. How would you measure the density for solid objects and for density in a liquid? Now in this case, I already know the definition. This is mass per unit volume, and this is your equation. And again over here, the density actually has its own symbol, that is rho. Cursive P. Density can be measured in terms of two possible units, that is either kg per meter cube or centimeter gram per centimeter cube, right? These two units, but obviously they should not be combined in any format. Like kg never goes with centimeter, gram never goes with meter. They're always going to be in pair, kg with meter, gram with centimeter, right? So this is it, and let's understand these points now. Over here it says that use a balance to measure its mass. This will give you the mass of the object. And then if it's a regular solid, start by measuring its length, width, height with an appropriate piece of equipment, basically a meter ruler. Then calculate its volume using the relevant formula for that shape. For example, if it's a cube, then use length into length into length. If it's a cuboid, then use length into breadth into height, right? Basic formula for cube and cuboid. Other than that, if for an object is an irregular object, you have to find its volume by submerging it in a measuring cylinder filled with water. The water displaced by the object will be transferred by the object, and this will be referred to be the volume of the object. For example, what this statement indicates is that, for example, you have measured that originally you have filled out your measuring cylinder up to 50 centimeter cube, okay, and after submerging that object into that measuring cylinder, the volume had risen up to 60 centimeter cube. That means over here originally it was 50, now it is at 60. That means the change in velocity will give you the volume for the, like, change in volume over here of the water will give you the volume of the irregular object. So that means the change in volume of the water body, or change in volume of the water displaced, gives you the volume of the irregular object. So this is what written over here, that record the volume of water in the measuring cylinder. This is the volume of the object. Input this into the data, which was equation, and then this will give you the value for your density. So from this case we understand that change in volume of water displaced is equals to volume of object. Right, as over here we are displacing water, that's why we refer to this method as displacement method. In your question paper, this is a very repetitive pattern. They would ask you to explain what is displacement method. This is the displacement method. And then again, density for liquid is also asked, but not that much common like the one in solid. If you guys watch the Big Bang Theory, then I think Sheldon has obviously explained this displacement method much more clearly than I did, right? I think it was in season 5 or season 6, I'm not sure, but there Sheldon was explaining facts, and then Sheldon said the displacement method in very much detail. I do not have the clip for it, but I think those of you who watch Big Bang Theory, we obviously love Sheldon for explaining us physics in much more easier and fun learning way. Okay, back to physics now again. Now this one is to find the density of a liquid. Similar process. You place a measuring cylinder on a balance and zero the balance. Over here we first will measure the weight of the measuring cylinder and then measure that cylinder again filled with water. Okay, so pour 10 ml of water into the cylinder and record the liquid's mass, and then this is mass 2, this is mass 1. If you subtract this mass 2 from mass 1, this will give you the just mass of the liquid, right? Over here this is what? Just the mass of cylinder. This is mass of cylinder, and this one will give you mass of liquid plus cylinder. So if you can subtract both of them together, that will only give you the mass of liquid. After that, pour another 10 ml of the measuring cylinder. Repeat the process until the cylinder is full, recording the total volume and mass of each time. This is for making the entire experiment more accurate. That's why we're repeating the data. And then again, for each measurement, use the formula to find the density. Remember that 1 ml is 1 centimeter cube. This is again very important, the conversion unit. And lastly, finally, take an average value of your calculated densities. This will give you a value for the density of the liquid. And this is again a very detailed answer of how to measure the density of a liquid and how to measure the density for a solid. Very important, this entire statement. After this, we'll move on to energies. Okay, now in energies there are non-renewable energies and renewable energies. Non-renewable energies indicates that they will never run out, right? They will never so non-renewable means they will run out, they will be used up, they do damage to our environment, and they provide most of our energy. That's why we are not even willingly we are using this, because there's no other option available. Examples are coal energy, oil and natural gas. And then for renewable energy, they will never run out, they are not damaging, and they does not provide much energy also. So examples are solar energy, wind, biofuel, water waves, geothermal, and hydroelectric. Very important list. Similarly, we use transport. I mean, transport can be used for renewable and non-renewable. These are renewable and non-renewable. Okay, very important topics. Which are the things we use? I would suggest go over this on your own. There's nothing much to explain from this energy chapter, so I just included this for the revision process. Okay, moving on. This is how these are the list of advantages and disadvantages for different resources. We have nuclear power source, nuclear power stations, then biofuels, then wind, hydroelectric power stations, tidal, and then you have geothermal, solar, nuclear. No need to take screenshot from the video. If you guys are interested, you guys obviously can get this file in my WhatsApp or in our Discord group. The link for the Discord group will be added in the description box. So yeah, this is it. And obviously this is my WhatsApp number, so you can also WhatsApp me or email me to get this file. I would suggest memorize all these things, memorize all the advantages and disadvantages for all the cases to get good marks in your exams. Yeah, other than that, conduction, convection, radiation, very important concept. Conduction means that the transfer of heat energy from one substance to another substance due to direct contact, and this is again for solid materials. Okay, convection is the transfer of heat through a fluid caused by molecular motion. This is for fluid, means gas and liquid. And radiation means energy that is transferred or transmitted in the form of rays or warm or waves or particles. This is for IR radiations. If you remember, IR radiations is infrared waves from the electromagnetic spectrum, right? IR radiations. Important definitions, these three definitions, I would suggest memorize that. And also there was some question about convection currents, like how convection currents is occurring, how conduction current is occurring, how radiation is occurring. Memorize that answer from the mark scheme points also. I could not add it over here, but remember that was a very repetitive question for all the question papers, like describe convection current, how convection is burning up the fuel or heating up the temperature of a room. This kind of question was extremely common from the old specification and in the new specification also. Okay, after this is your Sankey diagram. This one represents that how much energy is being used and how much energy is wasted. Over here, the arrows are actually of actual length. You cannot just draw the arrows in random variations. For example, over here, I will consider this as 1000 joules of total energy. This is for your total energy input. Out of that, 20 joules was used in useful energy and 80 joules was actually used in waste energy. So in order to express that, how would you draw this on a not exactly a graph paper over here? I only drew this on a graph paper so that it's just easier for you to understand that lengths, the diameter of these wideness of these arrows are actually to a correct length over here. But other than that, how would you do the scaling? Over here, the scalings are done with 100 joule. In this case was done for 20 squares, right? 20 is basically what, 4 squares over here, I can understand. So maybe I divided that with 25 and got 4 squares, like 4 centimeter, because we draw this kind of graphs on 4 centimeter. And then again this 20 joule, wait 1 minute. No, actually I have to use one number and divide all the data with the same number. So I have 20 and I have 80. So what I will do is that I will divide all the numbers by, maybe this one by, this is 1000. Okay, so in that case, 1 minute, let me see what I can do. 1000 divided by 20. 25. No. Yeah, I will actually consider dividing all these things by 5. Okay, in that case, now not exactly 5. No, 5 doesn't. Yeah, okay, 50 then. Then we will have 20 centimeter for this 20 it will be 20 divided by 50. This will be 0.4 centimeter, and then again 80 divided by 50. This will be 1.6 centimeter. So what I will do is that I will draw this diagram with the diameters as 0.4 centimeter, this diameter as 1.6 centimeter, and this diameter as 20 centimeter. Okay, and then write down, on your diagram, or actually you will not write this centimeters unit. Okay, on your diagram you will just write down the amount of energy provided by useful section, waste section, and the total input. This is for your useful section. Okay, this is for useful energy output, this is your wasted energy output, and this is your total energy input. This is how you draw a Sankey diagram. And then this is the law of conservation of energy. Again, very important law, that energy cannot be created or destroyed, but it can only be transferred from one form to another. Okay, after this we're going to start with waves now. Okay, so for waves, this time we have two types of waves, longitudinal or transverse. Very important to understand their definitions, or memorize the definitions, that the vibrations or oscillations of the particles are parallel to the directions of motion. As you can see over here, the particles are actually vibrating in these directions, and the direction of the wave is also in the horizontal plane, right? So they're vibrating in the horizontal plane, they're moving towards the horizontal plane, so obviously the plane and vibration are parallel over here. For this case they are parallel, and in transverse wave they are vibrating perpendicularly, like up and down, and they are traveling horizontally. So over here for transverse wave they are perpendicular, right? That is the only difference between longitudinal and transverse. Another thing, there are a few properties that you have to understand, how to measure the wavelength and amplitude. For example, for this kind of diagram, for this kind of transverse diagram, it is very easy for us to understand how to measure the wavelength and amplitude. Amplitude is basically from the equilibrium position to the maximum position. That is the height of each wave represents the amplitude, and wavelength will be from either from one crest to another crest, right? Like this distance, one crest to another crest will be one wavelength, or you can also consider one throw to another throw to be the wavelength. And similarly on longitudinal wave, these are your points for rare compressions, and these are your points for refractions. As you can see, in compression the straight lines are quite tightly packed, and in compressions, so in refraction the entire lines are loosely packed, right? So you can consider from one compression to another compression will be your one wavelength, or from one refraction to another refraction, that can be also the length for one complete wavelength. Okay, and again for this there are two other quantities that are supposed to be measured. Another thing, there was also one thing that you need to measure is time period, like what was the time taken for entire one complete wave to travel, one complete wave to complete, right? Now there are actually two types of graph you will come across. The first type of graph is distance time graph, so displacement distance graph, and the second type of graph is displacement time graph. For example, this is your random wave I'm drawing over here. This is your displacement distance, and this is your displacement time graph. Okay, from this first category graph, displacement distance graph, you can find out amplitude, you can find out wavelength. But from your displacement time graph, you can find out amplitude, we can find out time period, and using the formula for frequency, you can also find out frequency from this case. Always remember, you cannot find out time period from the displacement distance graph, and you cannot find out wavelength from the displacement time graph. There are two different types of graphs. Okay, this is first graph, this is second graph. Very important to understand the difference between these two graphs. Okay, then again, this is a frequency, this is the number of waves passing through a point per second, and its unit is hertz. This is again named after the scientist, so this is your SI unit for hertz, frequency, and base unit would be 1 over second, or that is s power minus 1, that is your base unit for second. And then again you have wave speed, v is equals to f lambda. There is one derivation related to this also. Originally your equation is v is equals to dt, Okay, in that case, over here the distance traveled is lambda, right? So what I can do is that I can write the equation d multiplied with 1 over t. In that case, now I can write that distance traveled is one complete wavelength, so d becomes lambda, and 1 over t is frequency. So this is a derivation from normal constant speed equation with wave equation. Also, this includes one thing, that v is equals to f lambda can only be used when the wave is traveling with constant speed also, right? So assumption for this case also is constant speed. Okay, other than that, now this chart is very important. Nothing too important about what other things and all. You just have to memorize the names, 7 names: radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma rays. These are the rays, or these are the waves that you should remember. And then again, what happens is that down the group from radio to gamma, your wavelength decreases, right, but frequency increases. So over here, one of the two criteria for this entire chart, I should write this like this: radio, micro, then infrared, visible, ultraviolet, X-ray, and gamma. Down this group, lambda decreases and frequency increases. Very, very important to understand this pattern. Other than that, nothing is important from this section. Okay, then starts your refraction. Very important concept again. Refraction and total internal reflection. Okay, other than that, what we have? Echoes, right? For sound system, we have echoes, and then a quick question, right? Okay, then we'll start with refraction. This is basically the bending, sorry again, typing mistake, I'm really sorry. This is the bending of light when light changes medium, that is known as refraction. Always remember, in refraction, the speed and your what is this, wavelength changes, frequency always remain constant. Okay, so in refraction, speed and wavelength changes, but frequency always remain constant. Okay, very important part. Then again, over here, in this case, how would you know that in which direction the light will bend, right? Is it going to bend towards the normal, away from the normal? I do not know, right? I mean, I cannot guess that, obviously. How would I understand that? That is because over here, this is how refraction occurs, by the way. 1 minute. This is your incident line, this is your normal line. Normal line should always be dotted, like drawn with the dotted lines or broken lines. And original rays, that is incident, reflected, and refracted ray, should be drawn with solid line. And this is the angle they are creating. The angle should always be measured with respect to the normal. That means you are going to measure the angle like this. This is the angle of incidence, this is the angle for reflection, this is the angle for refraction. We never measure the angle with respect to the boundary. This is not going to provide you any angle. Okay, so in all the cases for refraction, reflection, the angles should be measured with respect to the normal, not with respect to your boundary. So that is again one point. So always has to be measured with respect to normal. And then again, how would I understand in which direction the wave should be bending towards? So this is the case. Then again, I'll draw a chart over here. Okay, so over here, in low dense medium and in high dense medium. Okay, Like this one will explain that what happens when your ray of light enters the low dense medium and what will happen when your ray of light enters the high dense medium. Over here, when your object enters the low dense medium in this section, and low dense medium, resistance is less. Okay, so object can actually travel with a higher speed. So over here, speed is high. For higher speed, as we know that speed is directly proportional to wavelength, wavelength will also be high. Okay, so in this case, if wavelength increases, the angle of incidence increases. That means your ray of light will move away from the normal. So higher wavelength indicates that in low dense medium, ray moves away from normal line. Okay, and the opposite happens in high dense medium. Obviously, in high dense medium, they have a very low speed. For very low speed, again, velocity is directly proportional to wavelength, so wavelength will be low, and in this case it indicates now ray of light moves closer to normal. Okay, so this is how I will understand that in which medium, in which direction the ray of light should move. This is not prediction, this is entirely understanding that in low dense medium, they have high speed, so high wavelength, so ray moves away from the normal. In high dense medium, they have low speed, low wavelength, so ray moves closer to the normal. Okay, this is very important to understand or describe entire refraction concept. Other than that, let's move to total internal reflection now. Okay, so for total internal reflection, it says that when light passes from more dense medium to less dense medium, it is totally internally reflected. This is one of the conditions or laws for your total internal reflection to occur. The light must travel from more dense medium to less dense medium. This is the law. Light must travel from high dense medium to low dense medium. Okay. Now after this again we'll start. It says that total internal reflection over here occurring in 3 different sections. This is actually how total internal reflection is connected to critical angle. Okay, now sometimes people think that critical angle itself is a different quantity, but no, critical angle is just a fancy name for incident angle. Let me explain you why. Now over here, this is your scenario 1, this is your scenario 2, and this is your scenario 3. Okay, so in this case what happens, this is obviously the light must pass from more dense medium to less dense medium, right? So this is your medium 1, water, which obviously has a higher density than air. Medium of air is obviously less dense than water. So in that case, when the light is incident from under the water, it is going to travel from the medium of high dense, this is high dense, to low dense, right? So first already that like matching your criteria for total internal reflection. Other than that, what happens over here, now this time nothing will be reflected over here. Okay, everything will be reflected out, as we can see, right? This incident ray was interacting with the boundary, and then again it was reflected out. What happens at the next point is that when you start increasing this value for theta 1, angle of incidence, this angle of refraction also increases. Increasing means that refracted ray will move away from the normal or move closer to the boundary, and incident ray will move away from the normal and closer to the boundary. That's what indicates increasing the angle. Increasing the angle means the ray will move away from the normal. So in this case, if you keep on increasing the angle, this will also increase at that point. At some point, angle at like in this situation, after increasing the angle of incidence, this is the second scenario when the entire refracted ray is perpendicular to the normal or parallel to the boundary. Okay, this is a very important specific scenario. Scenario 2 is very unique. This time I know that angle of incidence this time will be known as critical angle. Okay, this is the value for your critical angle. Critical angle is entirely angle of incidence. It's just a fancy name for critical angle. And when does that object can reach critical angle? Whenever the refracted ray is creating 90-degree with the normal. Okay, so in this case we know that critical angle can only be achieved if your angle of R is perpendicular I'll just write the perpendicular sign. Okay, perpendicular to normal, or you can also refer this as angle of R is parallel to boundary. I think parallel to boundary will just be confusing, because then you will again start measuring angle with respect to boundary. So just keep it to this point, that angle of refraction is perpendicular to normal. That means they will create 90 degree. And when after this point, when you will increase the angle of incidence furthermore, this refracted ray will now again enter the water medium, and that is when your total internal reflection is occurring. Right, this time I can express the total internal reflection in terms of critical angle. For example, in this situation, in scenario 1, total internal reflection is not occurring, right? We can write that this is basically the summary for them, that no TIR, total internal reflection, as your angle of incidence is less than angle of critical angle. Right, that is the scenario, that critical angle is angle of incidence is now less than critical angle, so reflection will not occur, refraction is occurring. Right, over here we are seeing refraction. In the second point, still no critical angle, when still no total internal reflection, over here no total internal reflection, and that is because angle of I is now equals to critical angle. Now they are equal to each other, and again over here also we are getting what? Refraction only. After this, the last part, this is your total internal reflection. Now we can see TIR, that is because angle of I this time is greater than critical angle. Okay, for total internal reflection to occur, angle of incidence must be greater than critical angle. These three statements are very important to understand, so I would highlight these things over here. Okay, now after this again, there's actually a relationship we have to understand, but I'm quite sure I don't have much space over here. Yeah, right. Okay, I actually need to explain refractive index and relationship between critical angle and refractive index. For that, oh wait, I have space over here. Right, I will use this space. 1 minute. Okay, so I was trying to explain the equation for refractive index and the equation for your derivation of refractive index with your critical angle. Now in this case, we are going to start the equation for refractive index over here. So for refractive index, in this case, for example, always your light must travel from one medium to another medium, right? So I'll draw a very small box over here. So your light was traveling from this medium, wait 1 minute, from this medium, and then got refracted obviously along the way, and this is your normal, very small diagram over here. In this case, the actual refractive index come from with this understanding, that refractive index of first medium multiplied with sine I is equals to refractive index of second medium multiplied with sine R. In this case, always remember, if your first medium is air, so the value for refractive index of air is always going to be 1. In most of the cases, what happens, in all of the situations, your light always travels from air to glass, air to water. So in that basic, this refractive index in 1 turns out to be 1, right? And you're going to get sine I is equals to n2 sine R. From this case again, if you want to find out the refractive index of the glass, usually, because I already know the value for refractive index of your air, in that case, then you're going to create this equation as sine I over sine R. That is how in your book the final answer or final statement is given. But I would suggest use the original process or original equation, which is n1 sine 1 is equals to n2 sine 2. In that case, whenever, I think it was in June 2021 question paper 1 also, that they were asking to find out the refractive index, but it was in the reverse way. Your object was traveling from water to glass, or from glass to air medium. So in that case, what happens, your n1 would not be 1 in that case. So that changes with the refractive index of water provided by the question. So always use this equation. N1 is always the medium from which the light is traveling. N2 becomes the medium in which the light is traveling towards, right? So let me just write this again over here. N1 is first medium, N2 is your second medium. And there's one derivation that we will understand now. The derivation is actually for critical angle and your refractive index. So I already know at critical angle, this is how the scenario looks like. This is the boundary. Perpendicular to the boundary is your normal, and this is your incident ray this time, and your refracted ray on critical angle will be entirely perpendicular to the normal, right? So this is the ray's direction again. This is your refracted ray. This is your incident ray. This is creating angle of incidence, and now this is your angle of R. For this case also, I'm going to start with this equation, that sine n1 sine 1 sine I n2 sine R. Okay, for that basic, now I have n1 sine I is equals to n2 sine R. This time I know it was traveling towards the air medium. That means n2 in this case turns out to be 1, which is the refractive index of air, and angle R was 90, which means that sine R turns out to be sine 90, which eventually becomes 1 again, right? So at this case, now you have n1 refractive index of the first medium or water multiplied with sine, not I, this will be C, because in critical angle, this is the situation for critical angle, right? Angle I becomes critical angle. Okay, so as I was saying, now n1 sine C, angle I this time is known as the critical angle, right? And this is now entirely equals to 1. n2 is 1, sine R is 1, so entire right hand side becomes 1. So now you have the derivation of sine C is equals to 1 over n. That is your final statement for your critical angle derivation. I hope this was clear for all of you. Wait, sorry, 1 minute. Okay, so we are done with the derivations for critical angle and for the equation for refractive index. Now we'll move on back to this part. Okay, that is it. Now let's turn with echoes. Echo is basically the reflected sound waves is known as echo, and in case of reflected sound waves, what does this indicate? This means now it will travel twice the distance, right? When sound is reflected, it is known as echo. It is used to locate the position of objects. Usually use ultrasound to locate the position for the fetus inside the womb, and then again we can understand how far we are from the sea level to prevent the accidents like Titanic. Right? For example, in this example over here, it says that a girl stands 100 meters from a tall building, clapping her hands each time she hears an echo of her clap. She is 100, so it takes 11.7 seconds for her to hear 20 echoes. Calculate the speed this time. Okay, now over here it was 20 echoes, right? And this was your value for the total time. And it was also stated that she was 100 meters away from the building. So this is how the entire thing is working. This is entirely the building, and this is your, I cannot actually draw girls properly or anything, so this is the sound traveling and then coming back. We can clearly understand this is one D, this is another D. Now over here they are traveling twice the distance. Since they are going to travel twice the distance, now we are going to have V is equals to 2D by T. And then again we had this for 20 echoes, right? So 2D multiplies with 20 becomes 2D multiplies with 20 divided by time. And that's what they did over here. D, 2, 20 and time. So you're going to get the value for your sound speed as 342 meters per second. This kind of echo calculation is extremely important. They would ask you in both paper 1, paper 2. Quite very repetitive questions from this concept. So yeah, this is it for your sound waves, or all waves actually. That is all the things that you need to remember for waves. So let's move on to a very quick question now. Okay, in this question, this is question 4 from a certain year. Now it says that ground penetrating radar uses radio waves to detect changes in material underground. See the formula linking speed, frequency and wavelength. This is it. Speed, frequency multiplied with wavelength. Okay, and then again GPR radio has a frequency of 170 megahertz. I have already stated that mega is 10 to the power of 6, and the speed of sound is, this is actually a typing mistake, this is 3 into 10 to the power of 8 meters per second. You need to find out the wavelength, that is basically what, frequency over speed divided by lambda. That's 170 into 10 to the power of 3 into 10 to the power of 8 over 170 into 10 to the power of 6. Right, yeah. If you calculate that, that will give you the value for your wavelength, frequency. Now then again, obviously frequency in hertz, right? Okay. Then again, in radio, a radio wave passes through a ground and refracts at the boundary between soil and rock. The diagram shows 3 wavefronts of the wave before and after refraction. The wave also reflected at the boundary between the soil and crack. Complete the diagram to show 3 wavefronts after the wave has been reflected at the boundary. Obviously, this is how they will be reflected. And as we also have to draw the wavefronts, this is how the wavefronts will be. Okay, this is exactly everything you need to draw. Other than that, nothing else. Okay, then again explain why the radio waves passing through the rock have a smaller wavelength than the radio waves passing through the soil. Okay, 1 minute. This was soil and rock. I mean, basically they're asking that why the refracted wave has smaller wavelength than the reflected wave. That is because of the case for diffraction, right? In soil, they have less density than in rock. At higher density, speed decreases, so wavelength decreases. So we'll write that soil in rock, which is a high dense medium, and so does the wavelength. Okay, so yeah, with this our entire waves comes to end. Let's move on to electricity now. Okay, so for electricity, these are the things that you need to remember, that what would make a plug suitable or less suitable. There are 3 wires. Green represents earth wire, red represents live wire, blue with neutral. And these are your points, that fraying cables, why are they wrong? Because there is a potential chance for being electrocuted. Then long cables, a tripping hazard might occur. Then water, because they are good conductors of electricity, so can obviously electrocute the user. And then this diagram is extremely important. You need to understand with what position there's a fault in any case, right? This is the perfect plug, and there will be other faults in the plug which you have to understand, which you have to identify. Okay, and then again, these are the 2 safety devices that you need to memorize. Safety devices. For the first safety device, you have fuse. You need to understand the wait 1 minute. Yeah, this is fuse. The entire electrical symbol for fuse is like this, a entire cylinder, a rectangle over here, and between them they have a wire passing through them, right? This is again a very important definition for cylinder, that in cylinder over here, not in fuse over here, it says that a fuse is made up of a thin wire that melts at high temperature, and this causes a large current, this prevents a large current to passing through the appliance. So it sacrifices itself to prevent creating explosions or harmful to that, creating or destroying that appliance over there, right? And then again we have earth wire. Earth wire is again same, it provides an alternative pathway with lower resistance for excessive current to flow. Okay, and then again after this, current is the rate of flow of charge, and current flows from the positive terminal to the negative terminal, right? From the positive terminal to the negative terminal of the battery. This is also the conventional current flow, right? Conventional current flow. Very important to understand again, because in your exams tomorrow they might ask you to show the direction of conventional current flow on a circuit that is basically current moving from plus terminal to minus terminal. Okay, other than that, then again you have double insulation, that both the wires inside and of the device and the outer casing of the device are insulated, so no chance of electrocution. Now usually we use plastic materials for double insulation, plastic or any kind of insulating materials. Okay, after this again, 1 minute, there are two types of circuit that you need to understand: complete circuit and incomplete circuit. So let's just draw a complete circuit over here. This is how a complete circuit would look like. This is your switch. Actually, when the switch is closed over here, this is your complete circuit. Okay, and we'll copy this and again paste it over here. When the switch in between the circuit is open, then it will be, when the switch in between them is open, now this is an incomplete circuit. Okay, so 1 minute, I'll just write this down over here. This is your complete circuit where there is no gap in between the circuit. This is your complete circuit, and this is your incomplete circuit where there is a gap in between the case, in between your circuit. Wait 1 minute. Now this is when the switch is open. Okay, you have to understand the terms also. When the switch is open, switch on or open, and this is the case when your switch is closed or off. Switch closed or off. These are the two important diagrams for electric circuits. After that again, these are some equations very important to understand. Power is obviously what? IV. Then energy is energy, current. So this is actually a breakdown of this power energy time. Like power was already energy over time, right? Energy and power is also current into voltage. So in that case we can write IV. If you want to find out energy only, this one becomes IVT. That is the derivation of this equation. Then again you have V is equals to IR, the equation for Ohm's law, and equation for current. Q is equals to IT. Basically I refer to name this as QIT or QT, QIT. And then again this last equation, energy is equals to QV, charge and voltage, right? These are the few equations that are very important for your electrical circuit calculations. And then lastly, these are your graphs, extremely important graph. For example, first we have Ohm's law. Memorizing the Ohm's law is the first thing, that the current through a resistor at constant temperature. This is your assumption for Ohm's law, right? The temperature has to be constant. Constant temperature is directly proportional to the potential difference. It indicates that voltage and current are directly proportional as long as the temperature of that resistor is constant. Okay, or conductor is constant. This is your assumption over here. Assumption. Okay, now again proving that temperature remain constant, right? Again this was again highlighted, the temperature has to remain constant. Okay, so this is how the ohmic conductor behave at constant temperature, and this is how the ohmic conductor would behave with not like when the temperature is not constant. This is for non-ohmic conductors. Okay, this is for ohmic conductor and this is for non-ohmic conductors. I mean, it's not like non-ohmic conductors. For this case the temperature was changing, that's why it was not considered as a non-ohmic conductor. So this was the changing temperature. Okay, and then again we have three graphs. First one is for ohmic conductor, where it was already stated the current through the ohmic conductor at constant temperature is directly proportional to the potential difference as you get from a straight line. And then again the current for a current voltage graph for the filament. As the current increases, the temperature of the filament increases, so the resistance increases. Why does the resistance increases? That's because when current increases, the voltage increases, right? And when there is an increase in voltage, voltage and resistance are directly proportional. For that reason, in this case, resistance increases, and eventually resistance and current are inversely proportional. So for that case, less current can flow per unit, and so the graph gets shallower, or hence the graph becomes a curve. Initially it has high current flow, finally it has low current flow. That's because with time, with resistance, increase in resistance, current flow decreases. So in this graph, main baseline is going to be that current resistance over time increases, decreasing the current flow. Decreasing the current flow. And lastly, for diode over here, this is saying that current will only flow through a diode in one direction as shown, and the diode has very high resistance in the reverse direction. Also, this is your 0.7 volt. This is the minimum threshold voltage that has to be provided to your diode connection, otherwise the resistance is very high. Okay, the correct symbol for diode connection is this one. If your diode is connected in the circuit in this direction, then this is right. If your diode is connected in this direction, then this is wrong. Okay, correct symbol for diode connection. Okay, yeah, this is it. Then again we have light dependent resistors and thermistor. In light dependent resistors, light intensity is inversely proportional to resistance. So increasing light intensity decreases resistance. Okay, light intensity, I'll just write Li inversely proportional to resistance, and in thermistor, temperature is inversely related to resistance. Again, understand these 4 points, nothing very different, so I'm not saying all those things. Over here we're quickly moving on to circuit connections. Okay, there are two types of circuits, like arrangement of circuits. One is series, another is parallel. So for series connection, what happens, all the different components are connected in through one wire. Okay, so as all the different components are connected in one wire, their current remains same, but their voltage is divided. Using this basic, we can actually represent their equations. I already know current remains same. That means current for the total circuit is equals to current 1 for the first circuit is equals to current 2 for the second component, right? For bulb 1, bulb 2 and the total circuit, they will all have the same amount of current. For your voltage over here, equation for voltage in this case now is going to be, I know that they have same amount of current, right? But they do not have same amount of voltage. Voltage gets equally divided. So this is your total voltage, then voltage of component 1 plus voltage of component 2. For series circuits, summation of all the voltage will give you the total voltage. And for the resistance also, you can break this down. You can actually get to the resistance equation through the voltage equation. So we'll start with voltage 1 plus voltage 2, and voltage can be broken down as what? I RT, I R1, I R2. Now as I already know, they all have the same amount of current, so I can take that I on the right hand side common, and then I'll have R1 and R2, which means these I gets cancelled out, and you are left out with total resistance is equals to summation of R1 plus R2. This is the equation for resistors connected in series. Very, very important to understand these equations or memorize these equations. Equation for resistors, equation for current, and equation for voltage. Extremely important. Then let's quickly move on to parallel circuits. For parallel circuits, again, in parallel circuits, each component is separately connected to the power supply. So over here, since they are separately connected to power supply this time, disconnecting one component doesn't really affect the other component because they are all in different branches. And in branches, these are your branches, by the way. In branches, current gets divided, but they will always have the same voltage. So over here, current is divided and voltage remains same. So we are going to start with our voltage equation first this time. As they all have the same voltage, voltage total, voltage 1, voltage 2, they all have this equal amount of voltage. But this time current is going to make the similar equation, that current total is equals to current 1 plus current 2. Right, and then again for that resistors, we can find out the equation for resistors this time using the currents information. So always remember, for series you use voltage to find out the equation for resistors. For parallel, use current to find out the equation for resistors. So this is going to be I total is equals to I1 plus I2. I total is going to be what? I can be expressed in terms of voltage over resistance, right? So this is going to be voltage over RT, V over R1, V over R2. Similarly, again, we can take voltage common from the right hand side, or I can just write this also. These voltages were equal, right? So obviously they will be cancelled each other out, and now you are left out with 1 over RT, 1 over R1 and 1 over R2. This is your final equation. So always remember, in parallel circuits, the total resistance is equal to the reciprocal of the resistance, and total current is equals to the summation of all currents of the components. These are again very important points. Let me just zoom out so that you guys can see the parallel combination circuits equations and the series combination circuit equations. Remember these things for your maths that will come across in your exams tomorrow. Very important. Then again, lastly, we have static electricity. Static electricity is not that much difficult to explain or understand. Over here, this is all about charges that are not free to move. This causes them build up in one space and eventually creates a spark or shock. And then again, over here, very important one thing is that when insulating materials are rubbed together, negative charged particles or negatively charged electrons will move from one material to another. So it is always your negatively charged materials that will move, okay? It is never your positively charged particles. Always the negatively charged particles move from one case to another case. There are a few things to understand, that how can an object be positively charged or negatively charged. That is because, wait, let me see if I have written this in a file. No, I didn't. Okay, then. Positively charged means that it must have loose electrons. Now it has a surplus of plus charges, okay? It lost electrons now it has a surplus of positively charged charges, okay, which makes this entire particle, entire material as positively charged. Then again, for negatively charged, this time they got negative because by gaining electrons, and now it has a surplus of minus charges. Similarly, there are some repulsion attraction forces occurring in static electricity also. Minus with minus or plus with plus. In these both situations over here, they will repel because similar charges repel each other, okay? So same charges or similar charges repel each other. That means they will move each other away from each other. So they will move in different directions. and opposite charges is going to attract. Each other. These are the things which are important for your electrostatic forces. Other than that, nothing that much important. Obviously, they will ask you about inkjet printers, how they work, and yeah, gaining electrostatic energy through friction. That is one thing. Yeah, this is already written over here, gaining electrostatic energy through friction. This is for entire electricity and electrostatics. Now let's move to your magnetism over here. Very important and very large topic also, right? Now over here, magnetism is basically a magnetic material who has north and south pole, right? And they have this magnetic field through which this is a region through which other magnets or magnetic materials will experience a force. Okay, and this is a diagram. Obviously learn how to draw this diagram. Again, there are actually 3 to 4 field lines of diagrams. Like how would you create uniform field lines, how would you create how would the field lines be for north and south pole, how would the field lines be for one magnet, how would be the field lines for similar magnets, right? There are actually 4 diagrams. I want to draw the diagram, but I don't think I have kept enough space, right? I think I will use this space over here to draw the diagrams. So let me just write all these things in a very small space. Okay, so these are the 4 different arrangement of magnetic field lines that will be asked in a question. This is for uniform field lines, where the lines are at equal distance and parallel to each other. This usually creates or forms in between the north and south pole for 2 different magnets. This is the north pole magnetic field lines, where they will obviously repel, but these ones are quite too similar, like right, north poles and south poles magnetic field lines. Only difference is that over here field lines are moving away and field lines are over here entering the magnet, because north pole is basically the one who is generating the field lines, and south pole is going to receive the field lines. And lastly, for around 1 bar magnet, this is how the arrangement will be: away from the north pole into the south pole, right? This is how the field lines will be generated. For every cases, I would suggest at least draw 3 magnetic field lines for all the 4 diagrams over here. Okay, after this then again these 2 parts are quite important, that how to find out the overall shape of magnetic field lines and direction of magnetic field lines. Always remember that the shape of magnetic field lines can be understood by using the iron fillings, but iron fillings can never give you the direction for the field lines. So for the direction and shape, you can use the experiment with compass. These 2 descriptions are extremely important. There are high chances that they would ask you to describe these 2 diagrams or these 2 experiment to identify the direction and shape of field lines. Very oftenly asked. And then again, if we move down, this is what types of magnets, that induced magnet and permanent magnet. Induced magnet is basically that this one, it will always have this magnetic material with or without anyone's presence. But for example, iron itself does not act as a magnet. For example, one iron bar will not attract another iron bar, because iron is a magnetic material, but that is not a magnet. These kind of magnetic materials under the influence of a magnet act as a magnet, right? So iron is a non-magnetic iron is a non-magnetism. I mean, this is not an entirely magnet. It has the properties of magnets that can be only arised whenever the iron bar is close to one of the other permanent magnet. Like iron over here is not an actual magnet. It has magnetic properties, but that can only be induced or influenced in the presence of magnetic field lines of a permanent magnet. Like permanent magnet doesn't actually depend on any other magnets over here, but your induced magnets, they do depend on other magnets. In presence of only other magnets, they can act as a magnet. That's what they indicate about induced magnets. Over here, this is the statement that permanent magnets produce their own magnetic field, whereas induced magnets are magnetic materials that turn into a magnet when they are put into a magnetic field. Outside the magnetic field, they are not going to act as a magnet. Okay, these 2 points are extremely important. I will put a star mark over here. 2 and 3. Okay, after this we'll start with electromagnetism. Similarly, understand the right hand thumb rule and exactly how a moving charge creates a magnetic field, and then again a solenoid over here. Okay, these two are extremely important. They would even ask you, like might ask you, that how these solenoids can create centrical concentrated circular field lines for a current carrying wire, and then again how a solenoid creates a current carrying, like a current carrying coil wrapped out in a circular coil shape, and how their field lines will be arranged. Over here, the main purpose of actually wrapping the currents in a coil shape is because in order to increase the field strength over here. In this case, the field strengths will be very low because the magnetic field lines are quite spread out, right? But over here, in this case, the field strength will be extremely strong because now they are quite close to each other. As we have already learned in the previous part, that magnetic fields, when they are going to be very close to each other, will provide a higher magnetic strength, higher magnetic force. So this is the case for actually using solenoids over here, or increasing solenoid over here. We can increase the strength of magnetic fields that a wire can produce by wrapping the wire in a coil called solenoid. That is the main purpose of actually using a solenoid, because we want to increase the strength of our magnetic fields. Then again, this is your motor effect, very important case. Motor effect is extremely important because in motor effect we are only using the force. Some people get confused between the motor effect and generator effect. Always remember, motor effect uses the force, and if you go down a little bit, this is going to be your generator effect, where generator effect entirely uses current over here, right? Generator effect uses the current, or it produces current, whereas motor effect uses the force to produce either sound or any kind of change that they want to produce. Always, I think, memorize the points for DC motors. These are the points 1, 2, 3, 4, 5, 6, and then again these are very important to increase the at which the rate the motor would turn. This is very important, the 3 points, and then again obviously these loudspeaker. I think I saw this question again in November 2023 also. So loudspeakers are extremely important. I would highlight all these points, like exactly how loudspeakers create sounds over here. Yeah, other than that, generator effect, understand generator effect and microphones. Microphone is basically the opposite of generator effect. Loudspeakers convert current into sound, and microphones convert sound into current, right? So loudspeakers entirely are controlled by motor effect. Microphones are controlled by generator effect. This is entirely important to understand the differences, loudspeakers and microphones. And then again, this is your transformer. Sorry, for this transformer. Okay, so over here you have step up transformer. Wait, again a mistake, I'm so sorry. This is supposed to be step up. Okay, this is step up and this is step down. In step down, this decreases the potential difference over the entire transformer, because this one has more turns in the primary coil than in the secondary coil, and this is your step down. This step down, so step up transformer increases the potential difference over the entire circuit. That is because it has less primary turns than in the secondary turns. In secondary turns, they have now more coils. Now for transformers, they actually have equations, 2 equations. First one is the ratio for the voltage and the number of turns. For example, voltage of secondary or voltage of primary is divided by number of turns in primary is equals to voltage of secondary divided by number of turns in secondary. You can use this to either identify the voltage of these transformers, or to either identify the unknown number of turns in any of the primary or secondary coil. And then again, there is another assumption for transformers, that is, transformers are 100% efficient. Okay. If they are 100% efficient, that means there will be no power loss, right? Power is conserved. So, if power is conserved, in that case, power for primary coil is equals to power for secondary coil. I can break down power as voltage into current. So, that will become voltage of primary multiplied with current in primary equals to voltage in secondary multiplied with current in secondary. This is again another equation. I specifically wrote it in this way so that you guys can understand that power is conserved over here, and transformer is known as 100% efficient, that no energy is lost for the entire transmission of electricity using transformers. Okay, this is it for your voltages. Again, like read these points overall, but other than that, nothing that much specific to explain from voltages or transformers over here. We'll move on to atoms. Now again, in atoms, I will not explain anything from this part. Obviously, neutrons is composed of protons and neutrons. Protons are positively charged, they are not mobile. Only the electrons are mobile. Electrons are negatively charged. Neutrons doesn't have any of their own charge, but they have their mass. Protons have their mass, electrons does not have their mass. These parts so sorry, these alpha particles, release of alpha particles, what exactly causes the change in alpha particles, these are extremely important. Understand these things over here. Alpha is basically what? Helium, right? With 4 neutron and 2 proton, and obviously it has a charge of +2. Beta over here is a negatively charged particle, so -1. And then again, this is for the beta particle release. Wait 1 minute. Yeah, this is for beta particles. Wait, made a mistake. This is for the release of alpha particles, and this is for the release of beta particles, and this is the equation that you can see. And lastly, for gamma rays, gamma is basically a radiation, so releasing gamma will not actually create any change in the neutron or proton number. Okay, the neutron and proton number is always conserved. Right, then you have quite important substance like statements over here. Half-life is quite very important to understand. What is half-life? This is half of the time for that radioactive material to reach half of its this is basically the time the radioactive material takes to become half of its original mass, right? So this is extremely important definition of half-life. This might come across in your exam tomorrow. And wait, not this one, I was supposed to highlight this one, right? This is your definition for half-life. And then there's one equation, like one graph over here that you can use to measure the half-life over here. This is basically how you can clearly see over here in this section that original mass was 800, right? When the mass was dropped down to 400, this becomes 2 seconds, right? Time was in seconds, and then again after that time was 4 seconds, right? Over here we can understand that this one has a half-life of 2 seconds, but every time it becomes half of its original mass and the time increases by 2 seconds. So obviously over here the half-life is 2 seconds. This is known as an exponential graph. For half-life, the graph will always be an exponential graph. It is already stated that if you plot a graph for activity against time, and obviously taking out the background radiation, you will always have a graph like this on the right. This is an exponential graph. Always remember, this is exponential graph. And the half-life found from the graph is finding the time interval on the bottom axis or the x-axis corresponding to have halving the activity of the vertical axis, right? This is it. And lastly, for nuclear fission, always most of the people get confused about fusion and fission. Always remember, fusion is not added in your IGCSE syllabus, okay? So you just have to understand these terms. Fission, fusion is your A2 physics concept, that is not in AS. Fission over here indicates that when a slow moving neutron is going to be absorbed by a radioactive material, right, then it becomes unstable and then it starts to decay. For example, over here you have uranium, this is your uranium 235. When a slow moving neutron attacks this, obviously this uranium accepts the slow moving neutron. Now it becomes 236 uranium, which is an unstable format of uranium. And now this unstable uranium will break down into krypton and barium, and also releasing some energy which is basically in the form of either heat energy and waves in the form of gamma rays. Okay, waves in the form of gamma rays, and then they are going to release 3 neutrons also. If these 3 neutrons are enough slow, they can also again attack another uranium 235, again create uranium 236 to make them split into krypton and barium, and again create 3 neutrons, as we can see, 3 neutrons, energy, and obviously gamma radiation. So over here in this case, the few things that you are supposed to memorize is that at every emission of uranium you are going to get 3 neutrons, energy, and gamma radiation. Then again what you can actually, this is basically a chain reaction. If the neutrons that are released are enough slow that can be absorbed by other uranium 235 particles, then this will create a chain reaction. In order to control these chain reactions, we have control rods, right? This is control rods. Control rods are actually they will absorb slow moving neutrons, so that eventually if there are no neutrons, obviously if there are no neutrons, nothing can be accepted by uranium 235, so there will be no 236 uranium, eventually preventing the chain reaction. So control rods are made up of graphite, and they actually control the process of your chain reaction, rate of your chain reaction. Right, other than that nothing else. You can actually read all these statements over here to understand the nuclear reaction, but this is basically all that is happening. Okay, whatever I said now, that is everything written over here using the mark scheme points. So this is it. All of the entire IGCSE physics comes to an end. I hope all this almost 3 hour 15 minutes was worth explaining all these things. And again, if you want to get this file, obviously this entire file will be provided to you. If you want the edited file, that can also be given to you. You just have to inbox me in my WhatsApp, or if you have to email me. Either of the cases I can actually reply to you in any of the social medias. Now again, I'm actually conducting classes for October 2024 IGCSE physics, and our IGCSE classes for May 2025 will also start from July, I think, and we are going to start our AS classes obviously from June 20th, right? So I would expect, if you guys like this video, if you guys understand my explanations, and if you guys think that I can provide a better classes for you, so please join my classes from the next month for your AS levels, either maths and physics. Thank you for watching the video, and all the best for your exams. Bye bye.